Okay, I think we can get started. So thanks for inviting me again, Carlo, Matthias, and everyone. Alex, I think I was invited for the last 2 years as well, but it didn't happen. But it's good to be here after some time, for sure. I think before that, in 2019, I gave a tutorial also, which covered similar topics. But today we have a lot more going on. It's actually interesting that since 2019, a lot of things have happened on this topic of memory-centric computing and processing in memory in general. And I should also say that we have, I think, 4 hours scheduled. We don't have to do all 4 hours. We can, but I have material for 4 days or more. So that means we can do it, but we don't have to do it. It'd be good to get questions, etc., and some discussion maybe in this tutorial. I have. Say it again.
I'll cancel my hotel.
Hotel room. I see. Stay here. Yeah, sleep here. Okay, sure. That's another alternative, but I'm sure it's conflicting with other parts of the conference, right? Okay, so let's get started. So, as the title suggests, actually, I don't remember what's the title on of the tutorial on the Samos website. I think it's called Processing Data Where It Makes Sense or something like that. But I use the, let's say, less wordy memory-centric computing. Oh, this has increased. Something happened. Maybe the door closed, or maybe I'm getting closer. I'll use the less wordy memory-centric computing for this tutorial. And maybe at some point I'll ask you in terms of whether we go deep in some subject or whether we go broad in some subject. So this is meant to be a configurable or reconfigurable tutorial as well. Okay, so let's jump in. Let me give the lay of the land first. I think today it's clear to everyone that computing is bottlenecked by data. I'm going to put a lot of evidence to this later on. And data is really key for important workloads. Many people consider machine learning important today. I think it's certainly true, but there are other workloads that are important in addition to machine learning, like genomics and more classical workloads as well. If you look at all important workloads, they're all data intensive, and they require rapid and efficient processing of large amounts of data. And data is increasing. Basically, today we can generate more data than we can process in many, many domains. I'll give you some example domains very soon. Clearly, you may have examples from machine learning. I'm not going to dwell on machine learning as much, let's say. Data is increasing, and the things that we want to do on the data are also becoming much more sophisticated today compared to the past. We want to do a lot more things with the data. We want to mine the data. We want to do predictive analytics on the data. We want to discover many, many things based on the data today for good purposes and bad purposes. And I think always technology is agnostic to ethics, right? People want to do good things and bad things on the data. Hopefully, let's focus on the good. People are trying to do good things with the data. Even that's not easy today. So this is just one example. I'll start with neural networks, but so this is a talk that chief architect of the Cerebras systems delivered in one of our seminars in February. You can take a look at it. And it's on YouTube, actually. It's a 2-hour seminar. It's a beautiful seminar where they talk about their wafer scale engine to accelerate machine learning training. And I think it's a very nice example of what people are trying to do today to put compute and data, a lot of compute and a lot of data together by going wafer scale, making a chip essentially wafer scale. And this is the motivation, one of the motivational slides that he used, showing that the memory requirement of the models over the years, let's say, and the compute requirements of the models over the years. You can see that this is days. This is in terms of petaflop days, and this in terms of gigabytes. And they're both increasing exponentially, as you can see over here. So these are some of the latest models, and people keep introducing models. And the goal is to basically model languages, for example, do natural language processing, et cetera, very nice. I mean, clearly, this is one example where we have a huge growth of data. And as a result, models are also becoming more sophisticated, and they're pushing how much memory that we want to have and how much compute power that we want to have in our systems. It's interesting. You could of course take the contrarian view and say that, is it really worth putting so much effort in this direction. And I think that's a good contrarian view to have in mind. Probably it's worth exploring what we can do, but this may not be the right way of doing things right. But maybe we'll figure out the right way after exploring a lot of wrong ways, let's say. Okay, so that's machine learning, but there are a lot of other workloads where you can see similar growth of data pushing the boundaries of computing and memory today. So these are some example workloads. And if you look at these workloads, data is a huge performance energy bottleneck. And these are actually very interesting workloads. If you analyze, these are some papers that I referenced over here on the slide that analyze the issues related to memory in these workloads. And a lot of these papers show that in these workloads, memory latency, bandwidth, and capacity become bottlenecks. And sometimes they're all bottlenecks at the same time. So there are a lot of bottlenecks here, and they affect performance and energy significantly. If you look at some other workloads that are on the mobile end, which we're exercising right now, actually, I think right now we're doing video playback and capture using Zoom. There's some web browsing going on. There's some inference going on, whether or not you want it. Somebody's doing some inference on your data or training on your data as well. And these workloads, the mobile side of the workloads, are also bottlenecked by performance energy. I say mobile side over here, but some of these also are employed in data centers, clearly. There's huge video processing that goes on data centers, for example, on YouTube, when you upload or download videos. Okay, I'm going to give you some more data in terms of how this overwhelming happens. But before, I want to take a little detour on some important workload that, or important area that I believe is really interesting. And this is genomics, basically. And here we see data really exploding. And the reason is technology is developing very fast, meaning there are genome sequencing technologies that are extremely low cost today compared to the past. And this is a famous picture that NIH has. It's a bit older version of this picture. But if you look at this picture, what this shows in this blue curve is the cost of sequencing DNA. And you can see that it's exponentially reducing. This part is log-based, let's say. And this other curve, the white curve here, is the cost of a transistor as dictated by Moore's law. That's also reducing exponentially, but the exponent here is much, much, much larger, as you can see. And the reason is around this time, high throughput sequencing technologies were introduced. They were much better than prior type of sequencing technology. So cost dropped dramatically and kept dropping. And toward the end over here, at the end of the timeline, nanopore sequencing technologies were introduced, which is a completely different way of sequencing DNA or RNA. And that also dropped the cost significantly. And as a result, because of this cost reduction, we're seeing a lot of genomes being sequenced. And as a result, we can hopefully have more scientific discoveries, medical advancements, etc. But basically, if I have to put this picture in context, we have sequencing devices that are extremely powerful. They chop the genome into pieces. And in the end, we want to have scientific discoveries. We want to have a better understanding of COVID-19, for example. We want to do predictive analytics on figuring out what kind of variants may come about, where, before they come about. Or we want to give a device to the doctor, and the doctor can say, do your DNA analysis. And they basically figure out what is your vulnerability to a particular disease very quickly. Or they figure out what kind of drug should they administer to you personally so that you get the best benefit out of a treatment. These are interesting questions, scientific and medical questions, that are essentially limited by these steps, computational steps, essentially, that are required to analyze the genome that comes out. So this is one place where we can go deeper. We can actually go into this genome analysis deeper after we cover the memory-centric part, if people are interested, and if you still have time, because I actually have a lot of material on this topic. We've been doing a lot of work on this topic. If you're interested, we can go deeper. So keep that in mind for now. But this picture is actually interesting because this is something I view as a data generator. This is a great data generator, and people have put a lot of effort into building the technology for these data generators. And the goal of any data generation in the end is some sort of insight, either scientific discovery or some application. We're basically great at data generation, but we're usually very bad at data analysis, I would say today, because our data analysis engines are very slow and inefficient. Okay, so keep that in mind. And this is the example technology that I showed you earlier. This is a nanopore sequencing technology. You can see that it's very small and cheap. You can buy these devices and you can actually do your own DNA or RNA sequences. These were some of the first devices that were shipped all over the world to actually sequence the COVID RNA And they enabled a lot of understanding of this. So it's great technology in the end, but there are a lot of computational bottlenecks. So we have written a lot of papers about it. I'm not going to go into the details of it, but I'm mentioning this to you as an example application where data is really pushing the boundaries today. And if you want to do sophisticated analyses, for example, on critically, there are many case studies in medical field. For example, if you want to do some sophisticated analysis on a critically ill infant, it takes 2 to 3 days or 4 to 5 days today on a data center. So this is a great data generator, but data analysis, it's a terrible data analyzer. You have to move the data somewhere else to do the analysis. It could be a data center. That's what's been happening also. When you sequence like the COVID RNA, for example, you do the data analysis in a data center, right? Especially if it's a sophisticated analysis. And 4 to 5 days is not acceptable, basically, in many cases. It's just too late, too slow. Okay, so I think this is the major point. We have special purpose machines for genome sequencing in this particular case. It's very good at what's doing. It's extremely fast. And we have general purpose machines for analysis in general, and they're very slow as a result. And we have to move the data to this general purpose machine. And this talk in general is about keeping the data as much as possible to where it's produced or where it's stored. That's, in my opinion, what's memory-centric. So while you're sensing the data over here, maybe you should do the analysis over there as well, as opposed to killing some poor machines, let's say. And as a result, a lot of performance and energy. And this picture, I think, is representative of many data generators we have today. So you can take the example of video, right? We have all video cameras all over the world, and people actually do very sophisticated analyses on video today, but the same picture exists. We have extremely sophisticated, very good cameras, but we basically process what comes out of it in usually general purpose machines that are quite far away. And you can put your favorite data generator over there if you're interested. Okay, genome analysis is something that's very close to my heart. I can talk about it more, but if you're interested, you can read some of these works that we have written that mainly talk about data as a bottleneck, but we do to overcome this bottleneck, we do a lot of design, algorithm architecture, co-design. This is one example where we did FPGA-based near memory acceleration of genome analysis, as well as weather modeling. I'm going to mention some results just to motivate people from the get-go. So this is actually on a real system. So in a sense, it's not as forward-looking, let's say, because it's a real system, right? You're limited to what you can do in a real system. But even with a real system, what you can do is you can take a genome sequence analysis workload, pre-alignment filtering in this particular case, state-of-the-art, put parts of the algorithm into the FPGA. And the FPGA is much closer to memory than this state-of-the-art GPU is. As a result, it has high bandwidth, low latency access to high bandwidth memory. And if you actually put the right logic over there, and if you offload the computation, you get significant improvements in terms of performance and energy in weather modeling and genome analysis. So these are some sample results from the paper. You can see the performance improvements on a real system compared to a pretty hefty CPU today is quite high. It's in the best cases, 2 to 3 orders of magnitude, right? Performance energy. And this is not a trade-off between performance and energy, right? This performance improves, energy also improves. So if you want to actually compute the energy delay product, that improves even more. Right? Okay, keep that in mind. So our goal, I think, should be going into the future, improving both performance and energy. We don't want to run into the trade-off. Oh, I'm improving performance this much at the expense of this much energy. I think we should get rid of that mindset going into the future. How do we improve both performance and energy at the same time? Because I think we have a much bigger problem in our world today, which is sustainability. And if we actually go into the trade-off of performance and energy, we're not going to win the sustainability trade-off. We should really improve both of them. Okay, so as I said, I can talk more about genome sequence analysis, but these are some works that look at, for example, near memory acceleration of approximate string matching, near storage acceleration of again, genome sequence analysis. I'm going to talk about this as an example of near processing near memory in a little bit more detail. And this is a more recent paper that we published at ISCA just this previous month that looks at how to actually do both sequence to graph and sequence to sequence mapping, because genome analysis actually has different kinds of mapping techniques that you need to use as well. And this is actually quite interesting. But the future, I think, is quite interesting. As you can see, these devices are becoming smaller, and this picture is also old. They're going to become even smaller, and they're going to become better data generators, and analysis is going to be always difficult. Okay, I can talk more about this, and this is the part that we can decide later on if we have time. We can go more in depth into accelerating genome analysis. This is an older version of this talk. More recently, I gave another talk that actually covers a lot of research at ISCA. I'm happy to do that if we have time. I'm not sure. This depends on how many questions we get and how much time we want to spend here. Okay. So I think I picked this example because I think we have a lot of experience with it. And I think it's going to be a lot more important into the future. 10 years down the road, we should be, in my opinion, we will be the genome analysis will be everywhere, let's say. We'll see. But there will be many more applications in the future, and because people are dreaming, right? And people will develop more applications that require more data in the future. Is there a question, Carlo? Okay, sorry. It's hard to see from here. That's okay, no problem. maybe you're dreaming and a new application. That's yeah. Okay, so I think we'll look at some more applications later on, but let's pull back a little bit and think about what this sort of data growth is doing to our machines, at least the way we're designing our machines today. Clearly, our machines today are overwhelmed in terms of storage capability, communication capability, and in the end, computation capability. And we have actually quite powerful machines. We have the most powerful machines we have designed in the history of mankind, right? Especially for computation capability. We have the fastest CPUs, accelerators, etc. But they're getting overwhelmed today. And data also greatly impacts robustness, energy, performance, and cost. And I'm going to use this to motivate some processing near memory and in memory as well. But if you go back to the fundamentals, a computing system should have all of those components: computation, communication, storage, and memory. And over many decades, we've designed all of these, no question about that. But we've put a lot more focus on the computing unit compared to everything else, let's say, in the system. Basically, this computing unit, most of the time, it was CPUs over the course of, let's say, 8 decades. More recently, it incorporated accelerators like GPUs and other accelerators, more specialized accelerators, somewhat FPGAs. They're all computing units, in my view. They're designed for computation. So we focused a lot on it. Everything else is doing communication and storage. And this is an example computing unit, right? This is what a CPU looks like today, kind of. I actually drew this picture in 2008. It was from one of my first NSF, National Science Foundation proposals when I started at CMU. I think this picture is still very representative of what's happening today. But basically, this picture shows that you have cores in a computing unit. And those are the only parts that do computation, right? Everything else, caches, interconnect, other caches, other interconnect, memory controllers, other interconnect, memory, other interconnect, storage, other interconnect, etc. It's there for data storage and movement. And if you do the calculation, more than 95% of the hardware real estate of a single node is dedicated to data storage and movement. So we call this a computing unit, but it's really not a computing unit. If you think about like what's the fraction dedicated to computation. And if you look at the cores inside over there, a lot of it is really memory. There's register file, L1 caches. Nobody considers L1 caches memory, but they are memory. And other buffers, right? So basically, this is the state of a computing unit today. And this is because of the way we are designing our units, I would say. And you would think this computing unit is extremely good at handling data, right? Because clearly, most of the resources are dedicated for data. But unfortunately not. System is still bottlenecked by memory today. And I think this picture, we're going to get back to this picture later on, should make us think maybe we're doing something really bad in our systems to begin with, or really wrong in our systems to begin with. And that will be my thesis across this entire, let's say, tutorial. And if you don't believe me, let's look at a real picture. That's a real picture from an AMD, recent AMD processor. And this is L3 and L2 caches, basically. And there's a memory controller, interconnect, etc. So if you basically take out all of the memory parts, CPUs are 5% of the entire real estate. I'm not even showing the DRAM over here, right? If you put the DRAM over here, it puts everything in even bigger context. And storage, put that on top of it also. But I'm just looking at the computing chip. Okay. And this is not enough. We want to put more caches. So basically, those caches are not enough. We want to put more caches on top of it. I'm not saying anything about the technology. I think it's great that people are exploring this technology, 3D stacking, and trying to bond the chips in better ways, in faster ways. But the thinking is we want to put more caches so that we can tolerate memory latency more. And the question is, what do we get out of these caches? I think there are some interesting results on the internet that are floating around that say that on important gaming workloads, this cache, this additional 64 megabyte cache chip buys you about 15% performance. Does that sound good? Should we be satisfied by it? How much extra energy is this consuming? And how much extra, let's say, carbon footprint is this consuming? Let's say, right? You're producing this cache chip. And are you really doing the right thing by producing this cache chip in the entire system level? Okay, not just so that we don't pick on AMD, this is IBM. It's basically similar. And I could keep doing this basically for all of the processor manufacturers today. I actually do that in my course, but my course is longer, right? It's 14 weeks as opposed to 4 hours. Okay, and as a result, I think basically these devices are certainly trying to optimize for minimizing data movement somehow, from some perspective, let's say, by putting these caches, interconnects, etc. But they're not even doing that. And this study we did with Google, we analyzed essentially these workloads, these 4 workloads in detail. We may go deeper into the study later on. And this paper was published together with Google in 2018. And we found out that on these 4 workloads that many people commonly use, more than 60% of the entire system energy is spent on moving data across the memory hard on a state-of-the-art processor, basically. Okay, so we're going to get back to this. But I think before, now there's a question. Okay, sorry, I keep seeing your hand as a question, sorry. Next time I will not do the false alarm, so if you really want to ask a question, you'll have to shout or something. Yes, please. Okay, there you go.
So in the slide before you mentioned, I mean, I saw the layout from AMD machine. Okay, this machine has, let's say, memory from silicon via.
Oh, this one. Yes, this one. Huh?
So
sure.
Could you also, you are aware about the chiplet technology?
Yes.
So could you just, since you are the benefits
sure.
or the advantage or disadvantage of chiplet versus silicon via?
Yeah.
Just, okay.
Yeah, sure. I think, yeah, sure. That's a great question, I think. In fact, I mean, I see both of them are as quite beneficial in certainly improving the bandwidth between processor and memory, or between processor and processor, right? So chiplet technology, basically, I think of this as more like 2.5D connections, right? You basically connect different chips together with 3D. So I think the major difference is really 3D stacking, right? In this case, you have 2 different chips connected via through silicon vias. So the wires are certainly shorter than chiplets, and you can put more connections depending on the technology between the different chips. As a result, you get higher bandwidth and lower latency and lower energy, very likely, depending on the interconnect technology you use, especially with like future 3D stack technologies. If you don't use through silicon vias, for example, people are looking at more monolithic 3D technologies where you can reduce the size of the vias, or essentially they're like vias that you use on your chip. They become a lot more abundant, right? So they actually make the connections between the 2 chips in the third dimension much shorter, many more. So basically, I think in general, 3D stacking is lower latency, higher bandwidth, lower energy connections. I think the downside is certainly the thermal aspects, because you're basically stacking processors on top of each other. It could be a processor and memory also. Essentially, heat has nowhere to escape, right? As a result, you have a thermal problem, and you need to put more effort into cooling solutions.
Yeah, fully agree. But okay, in my mind, Apple has M1 processor.
Sure.
Chiplet technology.
Yes.
They selected. So I'm trying to understand why Apple's engineer decided to follow chiplet model than let's say this 3D model. Maybe the mobile phone, the application. Just this is a question. Sorry for.
No. I think it's a perfectly fine question. I mean, I don't know, of course, I cannot speak for Apple, but I mean, from my perspective, chiplets are easier to do from technological perspective. Right? It's less cost for sure, right? 3D stacking is higher cost, and also this thermal issue is not easy. So AMD actually has worked on this sort of 3D stacking technology for a really long time. They've actually done a lot of high bandwidth memory designs also in the past, so they have a lot of experience in this topic. I don't know Apple's experience, so I cannot speak for it, but it requires a lot more, in my opinion, expertise to do the 3D stacking and get it right. This 2.5D stacking or chiplet technology, AMD is also doing it, right? They're doing that as well as doing this. So I think chiplets are a step in the right direction and they have their place. 3D stacking is a lot harder to get to. And in the end, they will coexist, in my opinion, right? Because you have limitations in terms of 3D stacking, how many stacks you will have, perhaps, because of, again, fundamental thermal limitations. And to scale, you need chiplets. Sure. It's good. I think it's good to keep this interactive. Otherwise, I'll keep talking, which I can do also. Okay. Okay. So any other questions? Okay. Then I will maybe take another step back and then we'll go into memory-centric computing in a little bit. But I think I will argue that we need to design intelligent architectures going into the future. And unfortunately, I cannot call what we are designing so far intelligent. And there are multiple reasons for it. Because it's not handling data well, right? Clearly, most of its resources are dedicated to storing and moving data, yet we're really bottlenecked by data. So this brings the question, of course, how do we handle data well? I think we should ensure that data doesn't overwhelm the components we design via intelligent algorithms. I think algorithms need to be intelligent. Architectures need to be intelligent to bring this about. And perhaps more importantly, we need to customize whole system designs, algorithm architecture and devices together. So we're going to talk a lot about that later on in this part of this tutorial. But I think there are two other aspects which we may or we may not go into depending on the interest level of people over here. Is our systems are fundamentally not intelligent, meaning they're not taking advantage of data and metadata flowing through the system. Of course, this goes to how we define intelligence, but I think intelligence is at least in part defined by learning from experience, right? But our systems, hardware especially, but a lot of software also, does not learn from experience. I'll pick an example that I'm very familiar with, memory controller, right? I had an old phone. It doesn't matter. This phone I already have for 2 or 3 years right now, I think. It has a memory controller in it. This memory controller, its goal is to schedule requests, right? And it has a baked-in algorithm, heuristics based, designed by a human. And that human made some decision. And this memory control is following what that human dictated to do for 2 years, 3 years. If you have the computer 20 years, for 20 years. So clearly it's not learning from what's going on, right? It's making exactly the same decision all the time, regardless of the outcome of the decision. It's not even aware of the outcome of the decision. Is it correct? Is it not correct? Did it really improve performance? Did it hurt efficiency, etc.? So basically our systems are fundamentally unable to learn from their decisions. As a result, fundamentally not intelligent. I think we need to change that basically. We should really take advantage of the huge amounts of data and metadata that are flowing through the system and to learn from what's going on. I mean, an example of humans is when I interact with a stove, for example, if it's hot, I learned that I should not touch it again. That's basic reinforcement learning. I think we should have that basic, at least the basics of learning, bake it into our controllers and our systems. So if there's time, we can talk about that also. I have some more detail on that. Okay. The third thing is today's systems are not aware of the data and its properties. They're not communicated that information most of the time, and they cannot exploit the different properties most of the time, especially in general purpose systems. Special purpose systems, this is changing to some limited extent, but general purpose systems, what happens is different types of data has many different types of properties, right? Different data has different privacy properties, security properties, error tolerance properties, approximability properties, compression properties, compressibility properties, locality, something that we are very familiar with, different types of locality properties, yet that doesn't get communicated into the lower levels of hardware. And criticality properties, how critical is this particular request? And I'm going to pick an example from a memory controller again. Right? You have a memory controller that's trying to decide which request to schedule first. It may be from different applications. It may be from the same application. What it does today is very component aware. So it tries to make a decision by looking at, oh, is this row buffer open in this DRAM bank? Does this bank have a request contending, conflicting, etc.? Basically, all of these decisions are made based on the characteristics of the component that we're controlling, as opposed to characteristics of the data or the computation that we are trying to work on, right? Maybe a more intelligent memory controller would say, oh, I have these 2 requests. I think one of them is more critical because it's somebody told me that it's more critical, right? And this may be actually conveyed from the higher levels of the stack. It's a much more performance critical data. This information doesn't get communicated at all. Sometimes doesn't even get discovered at all in our systems. So basically, we don't understand or exploit the properties of different data in our systems. And I think these all three are important for building an intelligent system. Okay, these are the corollaries that I kind of talked about already. Today's architectures are not good at dealing with data because, as we will discuss and as we have kind of discussed, they're very processor-centric as opposed to data-centric. We're going to talk a lot more about this. But today's architectures are designed to make simple decisions, ignoring loss of data. They make human-driven decisions as opposed to data-driven decisions that learn and evolve based on that. And today's architectures do not know or exploit different properties of application data. They're mostly designed to treat all data as the same. As a result, they make component-aware decisions as opposed to data characteristic-aware decisions. And I think going forward, if we actually have all of these three, that's a good step towards some intelligent system. In this tutorial, I was thinking of covering the data-centric aspect, but if people are interested, we can certainly talk about data-driven and data-aware because I think these are also quite interesting. Any questions on this so far? Yes, please.
I'm just curious, will you discuss this intelligent design later? Not, I have a question. Yes.
You mean the data-driven design?
In general, the idea that you can actually learn something
okay.
from data and then do some smart decisions based on that.
I mean, I can discuss it later if you have time, sure.
My question basically
Go ahead.
goes in the direction is, are we really able to make some benefit out of it? Because obviously, you probably cannot configure the hardware, limited. Yeah. You'll have to do a lot of processing in order to make the decision itself.
Yes.
So there is an obvious benefit, of course, but you also have to make a lot of investment. That's your mind.
Sure. Yeah. So maybe we can discuss it in more detail, but my short answer is yes, you actually get a lot of benefits based on our experience with designing. So we've been designing, and other people also have been working in this area, but we in particular have been designing using reinforcement learning based memory controllers, prefetchers, and storage systems. And if you actually design the system such that it can learn from using reinforcement learning principles, you get a lot higher performance, higher energy efficiency, and also higher robustness in terms of the benefit, in terms of the performance benefits that you get. Yes, the decision maker, meaning the controller, is a little bit more complicated. No question about that. I mean, that's the trade-off, right? The hardware cost or the software cost. In storage systems, you can actually do that in software. It's easier. Is higher, but you can actually the latencies you can deal with. Complexity you have to unfortunately bite. There's no free lunch. I don't know if that answered your question completely. We can go into more detail in some of these techniques. But I believe the benefit is actually a bit higher than we can also quantify. Because what happens is sometimes, like when we do the experiments, we can only run so many workloads, right? And heuristic-based algorithms that we use can do okay in those workloads. But there's always some unseen workload that learning-based algorithms actually do better at compared to heuristic-based algorithms, in our experience, at least. If you set up the learning environment right. Okay, we can get back to it if you want. There's a slide over here toward the end of the tutorial that says we have no time for this, and that's the data-driven part. You can feel free to say there's time actually. Sure, you're welcome. Yeah, I think, yeah, that's part of it, certainly. I would argue that it's broader than that, but that's certainly part of it. I would say maybe, I don't want to pick neural networks only because I think there may be some issues over there, but learning from experience, let's say. I think that's, I believe that's part of intelligence for sure. And I think that's, yeah, yes, please.
Sorry, just a follow-up question. So on which level you actually have to do this? Because about zeros and ones, okay, you have to look at the level of the processes, you have to look at the level of debug data. On which level can you actually, you have to observe this in order to make some benefit.
Observe what?
Observe the execution of the program.
Yeah, certainly. So what we do, for example, we do it in the memory controller. Memory controller schedules some requests. And when you schedule a request, you get a reward based on the action you have taken. And you associate that reward with the state you were in. And over time, you learn to pick the requests that would lead to the highest reward given a particular state. Does that make sense?
Okay, so basically you don't go on the upper abstraction level, you talk about process ID, so you really just observe the state.
Exactly, yes. But you could, process ID could be part of your state, for example, or some process. Yeah. So I think when we get to it, hopefully we can discuss it. It'll become much more clear as to what's the state. Yeah. Yes. Mm.
The very fact that we bring in learning aspect, verification part of it, and then the second part was that schedulers are, you can make fancy schedulers, but what you sacrifice there is the latency. Make the decision making. Either for the initial traffic, you have to keep up on the scheduler. In the scheduler at the data front, or you give up on the latency.
Yeah. Yeah. Okay. There are two different questions. One is real time. How do you handle real time or predictable performance issues? And that's something that's, I think, open. I think people need to do more research on how to, let's say, in general, marry these let's say, learning-based schedulers with real-time guarantees. I mean, I can see some ways of doing that. There are actually some papers on that topic, but there's more that needs to be done. So you can adapt the environment so that the scheduler makes the right decisions given a performance deadline, for example. So it's possible to do it, but I think there needs to be more work in that area. The second question, what was it? Sorry. Okay, latencies. Yes. Okay, so latencies can be high. That's certainly true. Basically, my answer there is you have to adapt your design so that the decision-making latency doesn't become your bottleneck. In many cases, you can do that actually. Sure. Mm-hmm. Sure. Yeah. I mean, now we are going into all of those slides that I that I have in the later part of the tutorial. But basically, yes, there's a trade-off, right? Certainly, and the trade-off also changes the flow of testing and verification, and no question about that. I think design mindset also needs to change because now we assume that okay, we design a controller, and this controller we know exactly how this controller should behave in a given state, right? Maybe we should pull back a little bit from that because that is actually what we're arguing against here. Basically, because that's the human-driven aspect. Human actually dictates what the controller does. They know exactly what's going to do, and you can, as a result, you can exactly test it perfectly. Yes, it takes long even then, but maybe we should really start developing a new paradigm for testing more autonomous decision-making controllers, right? I'm not going to suggest that this is going to be, let's say, easy. It will take time, but I think that's perhaps something that's something we should invest in so that we can get to a better state, a more intelligent system. Yes. Yeah, I think that's a totally different thing, right? But yes, potentially. Yeah. I think the problem is actually a lot. I mean, there's a lot of work right now in explainable machine learning, right? I think people are actually looking a lot more in that direction. I think there's a lot of synergy between the testing and the explainable machine learning that people are trying to look into. Anything else? Okay, so we should keep moving. Well, we can get back to this. I have a slide essentially that covers all of these aspects that we discussed. including design mindset and testing and verification. There are upsides to this and there are downsides to this. This is to just the data-driven part of this. Nobody's asking questions about data or data-centric. Maybe those are not interesting. Maybe we should just jump into data-driven. What do people think? So who votes for data-centric going forward? Who votes for data-driven? Who votes for data-aware? Okay, I think I saw more data-centric votes. Maybe some people voted double or something. You voted double, right? I think I can. Okay. Yes, a real question.
Yeah, the question that I had, but since you mentioned, for me, data-aware, let's say, I think it's a superset of data-centric. Is that correct or not?
I don't.
I mean, you know, the notion is interpretation, the physical mean. Data-aware is superset of data-centric. So is that correct or not? Try to interpret what you have with your slides.
Yeah, I see. I think it's not a superset, but I think the distinction I have is you can make a computer much more data-centric without knowing the properties of the data. For example, if you actually process the data where in that sensor that does the genomic analysis, you can still put a processor over there and not know the properties of the data at all. Right? On top of this, you can know the properties of the data and make the computation much more efficient, of course, right? So I think that's the distinction I have in mind.
Yeah, of course, but this is the thing. I like very much the terminology. So it's very important because it creates an image.
Yeah.
It's a concept, actually.
Yeah. Data characteristic aware. That would have been much more precise, but that's too long. Yeah, I would really think about this as data characteristic aware. Okay, so let's keep moving on. Let's keep going. So I think to get to all of this, I believe we need to revisit the entire stack, especially the first one, but also the last one. The second one actually I think is a little bit different. The data-driven one, you can actually do a lot of local optimizations at where these different controllers exist. But even for cases where we need to rethink the entire stack, I believe we can get there step by step. So hopefully we'll talk about some simple examples as well, as opposed to huge examples where we just change everything in the system, right? But I think in the end, the goal should be to get to a better paradigm, you really need to change everything, right? Maybe not overnight, you do it over time. Okay, and this, I think I already said things like this. So, okay. Let me keep going. If you don't want to listen to any more of this, there are papers related to this. That's the purpose of this. If you want to zone out at any point in time, a lot of this is also already in papers, etc., that you can find. This is actually a very short position paper that they asked me to write for date, and you can find it online. But let's jump into the first part of it, which is data-centric or memory-centric part, since many people voted for it. You can change your mind if you want. Since this is a tutorial, we have a lot of freedom. Even if you look at data-centric architectures, I think there are a bunch of properties that I can list when I think about data and being data-centric, right? So in my opinion, data-centric is basically you center all of your decisions around the data. So if data is the most costly thing, you don't move it around, for example. And that brings us to processing data where it resides. And I think this is really important. We're going to talk a lot about that. But this also requires us to have low latency and low energy access to data as well. Oh, this is working better, I think, than my pointer. And these are complementary to each other. So you don't have to process data where it's reside, but you can reduce the latency and energy of your memory device, for example. Much better technologies, for example. I think we need low-cost data storage and processing. This is happening at some level. We need more of this. And we also want intelligent data management, like intelligent controllers handling robustness, security, cost, and performance, because data is really important, right? So let me talk about the first one. I'm going to talk about this last point also to motivate the first one a little bit. I call this processing data where it makes sense. That's the title of the tutorial, really. And this is to say that today you have no choice, basically. You have to move the data to a computing unit, processor, accelerator, CPU, GPU, FPGA. You don't have any other choice. You cannot process the data inside the memory, inside the storage, inside even the cache in the computing unit, basically. And this is an old idea. Basically, people wanted to move the processing somewhere else, do the processing, at least in part somewhere else. This is not a new idea, clearly. These are some of the oldest papers that I could find that I could actually pinpoint that this is actually really processing in memory. If you find something older, please let me know. I think it's a seminal paper. The other one that's actually very close in time is from Harold Stone, which you may be familiar with. He wrote a lot of textbooks on computer architecture. And he also wrote this paper on logic and memory computer. It was called logic and memory at those times. And later, somehow, it got renamed to processing in memory. And the terminology kind of got messed up. But hopefully, I'm going to offer a more clarifying terminology in this talk, as we have done in the past also. Okay, so the question, of course, you may ask is, this was proposed in the 1960s. Why it didn't happen, and what's different today, right? And that's what I'll try to motivate with first. I think today, basically, we have, I will basically summarize as we have no choice. Technology is not helping us much, and applications and systems are not helping us much. We're kind of getting squeezed in the middle. And push from technology is interesting because a lot of the technologies that we design for memory and storage are having problems. I'm going to pick examples from DRAM, especially dynamic random access memory. That's the technology that we have been building main memories with since 1970s. And it's been extremely successful, but it's having a lot of trouble today, especially in terms of reliability and robustness. And these are also causing security problems. And because of the difficulty in scaling DRAM industry, including the, let's say, slow-moving DRAM manufacturers are interested in doing something different with DRAM technology. And industry is very open to new memory architectures. So I'm going to motivate things from this technology perspective first, spending a little bit of time, and then we're going to spend more time on the system and architecture perspective and look at some memory-centric architectures. So this is, I believe these are the results of the technology scaling difficulties. People have formed like 3D stacking technologies. This is relatively old right now. You have a logic layer under memory layers, and logic layer may be connected with through silicon vias, or this is a better example, or some even denser interconnect technology. And people are pushing for even denser interconnect technologies and more connections between the logic layer and memory layers, and also intermixing logic and memory across these 3D stacking technologies. And I think this is a really good development. I believe all major DRAM manufacturers are doing this right now, and that's good. And people have been experimenting with other things like putting some simple, very which is interesting, but it's very limited computation. But more recently, if we were giving this tutorial in 2019, we wouldn't have this basically. UpMem, a startup, announced that they actually have general purpose processors inside the DRAM chips. This is actually very interesting. I think I'm going to talk about that later after we talk about adoption issues. So these are some real commercially available processing in memory chips you can buy today, and you can do real experiments. They're not extremely powerful, but they're the first generation. So it's very interesting, I think. It's real. And more recently, those, let's say, slow-moving manufacturers have also adopted processing in memory as well, and they're also targeting, advertising at processing in memories. We're going to talk about this more, but Samsung, SK Hynix, they both have prototypes at least. I don't know if they'll be prototypes, we will see. But they've announced these at ISSCC, the major circuits conference, with prototypes, saying that they have simple processing in memory engines in DRAM chips next to each bank of DRAM that can do some sort of computation. In Samsung's case, it's very specialized for machine learning inference. So it's able to multiply and accumulate, for example. SK Hynix is a little bit more broader, let's say. There are also other types of processing near memory engines where Samsung and Facebook announced that they have this module, huge DRAM, let's say, module that has some processing capability over here for recommendation system inference. And similarly, for the same application, actually, Alibaba announced a DRAM chip in this year's ISSCC, where they said that they built a DRAM chip with processing capabilities for, again, recommendation systems. So people are actually finding that the processing data where the data actually resides or gets to first after storage is becoming important. So hopefully, so I believe we will see more of this. And this picture doesn't include many other experimental chips and startups. So in this domain, since 2018 or so, there have been many startups also that have been trying to do things. They provide less information that they don't publish at ISSCC, for example, in general. So this, I think, shows us that something real is happening in this space. And it's not just because of the technology scaling. I gave you the technology scaling perspective very briefly. It's also because of applications. Okay, let's talk about technology scaling perspective. I think I'll go through this relatively quickly. But basically, we're having a lot of issues with technologies, DRAM technology in particular. And this is not news. I think we knew this starting from early 2000s, let's say. This is a paper that we delivered in 2013, for example, in the International Memory Workshop, saying that memory technology is not scaling very well. We should do something at the system level about it, meaning solve the problem with better controllers. If the technology is not scaling very well, we solve the problem with better controllers. And fundamentally, DRAM technology consists of a capacitor and then access transistor, right? And if you want to store more data, you want to have many of these DRAM cells, or reduce the size of the DRAM cell. And that's the technology scaling part. Reducing the size of the DRAM cell enables you to put more cells in a given millimeter square. But reducing the size of the DRAM cell makes it difficult to operate it reliably, because now your capacitor is smaller, as well as the access transistor is smaller. So they're both vulnerable to a lot of noise issues. Now, if we actually have a technology scaling tutorial, we could go into more of this, but I don't intend to go into it unless people want it. That's the other deep dive we can do. But let me give you some high-level results. So this is a study that we did with Facebook about 7 years ago. It's a study that took about 3 years, essentially, overall, to set up and to get the data. Yes? Oh, there's a question. Okay, sorry. Sure. Yeah, that's a good question. It's not comparable, I would say, because the way you measure that nanometer, even between different companies, between different, let's say, foundries, it's very different, right? And DRAM and SRAM is also quite different from each other. But I mean, if I have to give you a number, today at DRAM, we're around 12, 13 nanometers. But it's not comparable to what we see at 5 nanometers, for example. Yeah. Oh, I see. The cells are, you mean, bigger or smaller? So I think the cells are actually closer to what we have in 2D today in DRAM, yes. Because these are DRAM dies, it's very similar. Yes, so you can actually get a lot of density, but the thermal issues limit the capacity in the end. So you can, the 3D stack chips that you have today in DRAM are not as high capacity, let's say, as they can be. I think maybe I should say something. I don't know the exact technology nodes of the processing and memory chips that these folks developed. I think they may say that in the papers. UpMem, I know that they're working with an older technology. It may be 30, 40 nanometers. Yes. Yeah. For the processing and memory? Yeah. Okay, yeah. Yeah. Mm-hmm. Yeah, exactly. Yeah, I boiled that down to 12 to 13. Yeah. Yeah, somewhere lower and then one beta, etc. Yeah. They try to hide basically exactly where they're at. But again, their definitions can also be slightly different, as you said. Yeah, exactly. Okay. Yes, another one. Yeah, exactly. We're going to get to the system level perspective, but yes, a lot of these are accelerators today. Actually, all of these processing in memory chips that you see in this picture, they're accelerators. But in the future, it may change, right? Mm-hmm. Yeah. I mean, all of these have different ways of dealing with that. So for example, UpMem has an SDK, software development kit, that's based on C. So it's relatively easy to adopt. Let's say you need to specify where to offload your code, how do you move the data, etc. And then there's a compiler that handles that, yes. And some of the other ones are not public. So they claim some of them are, they're more seamless, let's say, but we don't know. Yes. I mean, I believe they're targeting more data center systems in their particular data centers, but I mean, they can also be scaled down to the public, right, in the future. But yeah, currently they're targeting these huge recommendation workloads that Facebook and Alibaba are processing in their data centers. Yes, one more. Oh. Who made the processor? Oh, Micron. Yeah. I think, yeah, for some workloads, yes. And I think people have explored it for genome analysis. We should probably ask Micron. Yeah. Yeah, there you go. But you cannot tell us that. They don't want to tell the world anything anyway. But yeah, I mean, I think it was a good experiment. I mean, I can imagine why. I mean, certainly costs, right? Cost could be one thing, but yeah, we can only speculate why it's that. Mm-hmm. Yeah, that's a possibility also. Yeah, maybe too early. Yeah. I mean, I have another theory, which is, I don't know. It's sometimes people do experiments like this and they don't see immediate success, and then they pull back and they become more conservative, right? I think we've seen that a lot in the DRAM industry, frankly. That happens a lot. And they feel they get burned, but they don't do the longer term investment. And I mean, maybe it's hard to do also, depending on the business constraints. I feel that way with automata processor. They basically didn't get the bang out of the buck that they put in. As a result, okay, done. We kill it. Worse than that. Yeah, okay, sure. Yeah, sure. Okay, so I was explaining this graph. Maybe it's not that interesting, so we can move on. But I think it's interesting. So basically, this is data from all of the servers that Facebook has at the time in all of their data centers. So it's a lot of servers, a lot of memory. And we basically wanted to understand the correlation between the density of the DRAM chip employed in these servers and the failure rate that you get at the server level. And there's a strong correlation, basically, as you can see in this graph. As the chips employed in the data center, these are running real production data center workloads, get denser, you see more server failures because you have more memory errors, basically, either detected or corrected. And maybe we don't have the uncorrectable ones over here, actually, because we don't know them. As a result, the system slow down or hangs or some failed, basically. So I think this is experiment from real data from the field showing that scaling is becoming much worse going into the future. And there's more work in that area that have repeated similar experiments into the future. And there's a lot of examples. I'll give the example of RowHammer very quickly. Basically, today we can probably people know about, how many people know about RowHammer here? Okay, I talked about it a long time ago here. So I'm not going to talk about it more. We can go more in depth because actually there's a lot of new things that are happening in RowHammer in 2020, 21, 22. Say it again. With the additions in the memory controller that didn't work. Yeah, not only memory controller, and the memory chips as well. Yeah. Actually, I think the memory controller would have worked out better than memory chips, DRAM chips. Yeah. Yeah, but basically, today you can predictably induce errors in DRAM memory chips. And it's because of the scaling problem, right? Essentially, if you hammer a row, keep activating, pre-charging. Basically, if you read a row today, you activate one row of cells, DRAM cells. This is a two-dimensional array of DRAM cells. And whenever you want to read a cell, you need to read the entire row, which means that you apply high voltage to the word line on the row, or open the row, or activate the row. And then you pre-charge the row so that you can read some other row. If you keep doing this repeatedly, it turns out cells in physically adjacent rows, if they're vulnerable to this failure mechanism, fail, meaning they flip from 1 to 0, 0 to 1, depending on the encoding. They lose data. Basically, your data gets corrupted. Clearly, this should not be happening, right? This should not be happening. This is a disturbance issue in memory. And it happens more today because cells are too close to each other. This toggling of the word line from high voltage to low voltage is causing failures in bits in adjacent word lines. Okay, so we call this hammer row, victim row. And in DRAM, especially in DRAM, this should not happen because most of our DRAM chips don't have error correction, right? And these errors are actually not easily correctable with simple error correction also. Okay, so essentially this is a problem affecting all manufacturers, and I'm not going to go into the details. There are a lot of security issues because now you can corrupt data, and this data that you corrupted may belong to the operating system, or it may belong to some other application. As a result, you may actually take over the system. There are actually really interesting security works in this topic. If people are interested in going into that direction, we can talk more about it. Okay, and people are actually writing articles that sound like this. I like this one because this person says, forget software, now hackers are exploiting physics. And I like it because this is really getting to the heart of what RowHammer is about. It's really a physics phenomenon, right, at the low level. But as I said, I'm not going to talk about it. But the point here is that scaling is hard, and there are problems that are happening, and we need to solve those problems. How do you solve those problems? The solution comes from adding slightly more intelligence to the memory controller, for example, and the memory chip, so that it's a little bit more aware of what's going on, right? If you look at this memory chip, you hammer it, and then bits flip. That memory chip is not intelligent because it just flips the bits, and it cannot even understand that something bad is going on. So I would argue that technology scaling issues are pushing us to be a little bit more intelligent, maybe not completely intelligent, but a little bit more intelligent, such that we can actually, these chips are actually able to fix these issues themselves or through a memory controller. That's why this is, I think, motivating us to do something more memory-centric in the overall system perspective. Okay, but as I said, we can talk more about it. And actually, if you want to have 10 years of RowHammer in 20 minutes, that's the, that's the talk to listen to. And this still doesn't cover the more recent research in this area. I think it's fascinating. So essentially, memory scaling issues are real. There are a lot of papers on it, which we're not going to talk about. This says a retrospective, but we need to update this paper actually, because there's a lot that happened since 2019. Let me give you another issue. So clearly, we're having a lot of technology scaling issues with memory. And I think it's clear to many people working in memory that we cannot solve all of these issues with a single technology. As a result, people are looking into putting multiple different technologies together so that you can have different technologies with different trade-offs, and you can design the hardware and software to manage the data allocation and movement between these different memory devices, such that you can achieve the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. And that's the idea of hybrid or heterogeneous memory systems. And again, this could be completely different technologies like DRAM, phase change memory, like magnetic memory, ferroelectric memory, pick your favorite memory technology. They all have different trade-offs. or it could be different types of DRAM, which is already happening actually. And I think we're pushing toward this direction. Why? Because this is enabling us to scale better. Even if one type of technology is not scaling very well, we are scaling the overall system better by adding different types of memory technologies and managing those different technologies better so that the overall system, overall memory capacity, for example, scales very well. And that's the idea. But for this to work, the controllers that are sitting over here need more intelligence, right? They need to understand the characteristics of different technologies, and they also need to understand the characteristics of the applications that are executing so that they can do the mapping intelligently. Okay, so I think that's another push from these circuits and devices or technology we're having. Okay, RowHammer, going back to, I think intelligent controllers actually have been proposed for RowHammer. They continue to be proposed. That's good, I think, that's great. Some of them don't work as you mentioned earlier. This is the one that works, I claim. We actually have the source code completely available. You can actually test it yourself. We have a security proof. Downside of these controllers is what we discussed earlier, right? The overheads. You need to pay some overhead to overcome these security or reliability or robustness issues in general. And again, I would say that industry is writing papers about it too. This is a paper that I would recommend to people if they're interested. It's from Samsung and Intel, two companies that don't normally talk to each other. They've written this nice paper in 2014. And they basically said DRAM technology scaling is difficult, and we should really be considering solutions that co-architect controllers and DRAM together to solve this problem. So it's very similar to what we have been advocating for a long time. And I think this is a step in the right direction also from industry. And that's good to see. And there are also controllers that, so if you look at the literature, there are many, many intelligent controllers proposed. This is one of the more recent ones that we designed. If you're interested, you can take a look at it. So existing memory chips are actually putting in undying error correcting codes, for example, inside. And they're hiding what they're doing from the entire system. And this is causing a lot of issues in the system today because the memory chip is correcting some errors internally. But when it's unable to correct errors, there are some issues that are causing the system because actually it may expose more errors to the system. So there are also some other issues. If you actually want to understand the memory chip's reliability characteristics, this on-die error correcting code is obfuscating what's going on underneath. Okay, so just to give you an example of like somewhat intelligent controllers that already exist, NAND flash memory. Today's SSDs basically are all using NAND flash memory, and NAND flash memory actually has all of these issues discussed, disturbance issues in a different way, of course, technology specific way, different kind of error issues. And this is a memory technology that essentially where most of the cells don't work if you don't have an intelligent controller. So you really need to have an intelligent controller that understands what's going on. I believe you need to do that with other technologies like DRAM as well. And if you're interested, we do a lot of work on NAND flash memory. I find this really fascinating. This is a survey paper that covers the technology in 2017. So it's a bit old right now, but I think the fundamentals remain the same. Yes. Sure. Yeah. Yeah. Not so actually things have been changing a lot. A lot of the flash controllers are quite hardware today, hardware and ASIC. Yeah, certainly there's software in it, but the critical ones, the critical latency critical parts certainly are a lot in hardware. But yes, I mean, your point is well taken. Flash has much longer latency still. And yeah, I mean, I agree. I think for DRAM, the problem is harder. Yes, you need to put, let's say intelligence, call it, in more carefully, right? Absolutely agree. So you cannot apply what you did for Flash to DRAM directly, for sure. And also for technology issues. Exactly, yes. Yeah, all of these are hardware actually today, because otherwise it's too slow. I mean, there are levels of ECC that are at the software level as well, but they're not the first levels. If you cannot correct it in hardware, then you actually pull to software. Okay, so emerging memory technologies also need intelligent controls. Basically, I think my point here is that all of the memory technologies that we're dealing with today, and probably very likely into the future, need intelligent controls. We have a lot of experience with phase change memory. I think it's fascinating. I believe Intel's 3DX point is phase change memory. I think hopefully there will be more phase change memory in our lives, but we'll see. But these technologies also need intelligent controllers because they all have very similar, in the grand scheme of things, reliability and robustness issues. Okay, I think the takeaway is that we need intelligent memory controllers so that we can avoid these failures and enable better scaling of our systems. So now let's jump to the systems and applications. It's great that people are asking questions. So any other questions? We're going a bit slow, but that's okay for me. Okay, so let's talk about systems and applications. And I think this is actually very important today. And it's always good to maybe ask the question, what if technology was scaling very, very well, but not systems and applications were demanding a lot more? Would we still need data-centric computing? And I don't know the answer, but I know that we're kind of squished in the middle today. So today, if you look at systems, data access is a huge bottleneck, energy consumption is a key limiter, and data movement energy dominates compute. I'm actually going to give evidence on all of these soon. But before, I think we should put things into perspective, because I think this is going to be a lot more important into the future. As computing professionals, we can perhaps fix part of the world's huge problem, right? We have a huge climate and sustainability problem. And do we want a world like this, or do we want a world like this is the question, I think. And that's going to become even more imminent as time passes with every second. Well, this may be something better than what's coming. I don't know. Let's see. But I think what I would argue is that we certainly want sustainability, energy efficiency, but we cannot give up high performance because a lot of the solutions that to issues that we're having can only be solved with high performance. So we really want all at the same time. We're very greedy as human beings. And I think we should not give this up. The question is, can we get all at the same time? Of course, I'm not going to, yeah. Sure.
The definition of high performance, of energy efficient, but please give us what is sustainable.
Yeah, I don't have a great definition, sorry. This is the sloppiness on my part. Yeah. Okay, that's, yeah, I think, I mean, sustainable, it goes back to this, let's say, maybe intelligence issue. Are we building hardware that actually is useful, or are we building hardware that's just sitting around and doing nothing? That's part of it, maybe, from my perspective. That's part of the sustainability issue, right? The waste, let's say. I think energy efficiency also goes into sustainability a little bit. Are you wasting a lot of energy that's causing a lot of trouble? But yeah, I think building hardware that goes unused, that's wasted, that's just twiddling its thumbs and doing nothing, is part of the sustainability also.
This term comes from, let's say, from a financial people, from the economy side.
Yeah.
Move, let's say, to computer architecture.
Yeah, yeah.
But I think you should define some
way,
or not have, let's say, not equation, okay, but should have some, have a way to measure.
Yeah, that's more difficult. So I think people are looking into, there are some work that's going on in this area in computer architecture. People are trying to measure the carbon footprint of computers. Maybe that's a measure, I don't know. That could be one measure potentially. So people are trying to do that for sure. So that's, I think, one direction. Sure. But I think maybe the example that I gave you from earlier, the AMD's 3D stacking chip, right? That chip, is that really useful? And if it's not useful, how much carbon footprint is costing us, right? Okay. I think energy efficiency goes into that equation as well. Okay. So I think basically the question is, are we doing the right things in our systems to actually achieve all of these at the same time? Basically, the problem we're having is that data access is a huge performance energy bottleneck. Yet our current design principles cause great energy waste as well as great performance loss. So basically, today we're designing our systems knowing that data access is costing us a lot. There's a lot of performance overhead of data movement, and we know that. But to overcome that performance overhead, and there's a lot of energy waste to do data movement, but to overcome that performance overhead, we make our systems a lot more complicated. We actually design a lot of software and hardware mechanisms to tolerate the latencies that we have, especially in the memory and storage hierarchy. Right? What do we have? We have massive amounts of multi-threading. out-of-order execution, heavy amounts of out-of-order execution, which is increasing actually in recent chips. I showed you the many levels of cache hierarchies, many levels of prefetchers were also in those hierarchies. Many different things basically that are complicating our systems. And many of the time, these techniques actually don't work. As a result, they compound the energy waste because they actually waste energy. If you have to query 5 levels of caches and only to find out that you need to get to memory to get the data that you want, you're actually wasting a lot of energy in your caches, right? Yes, you could try to develop techniques that bypass the caches, which is actually not an easy thing. But now you're adding more complexity to figure out when to bypass the caches. So I think it's good to think about the complexity that we're adding to our systems to overcome this data movement overhead. It's really getting us into a vicious cycle. We have this data movement bottleneck. We're wasting performance. We're wasting energy. To overcome the performance, we're wasting even more energy on top of that. And also perhaps we're wasting even more performance, right? Because to get to that memory access that you really needed to do, you have to go through 5 levels of caching. Basically, we're compounding our problems with the way we're designing our systems. And I think all of it is because of this root cause, which is processing is performed far away from the data. And I think this is happening at the micro scale, which is this micro scale that I'm showing you over here, but also at the macro scale, meaning if you look at a sensor, for example, you move the data from the sensor to the data center so that you can process it, and you keep moving the data all around. So essentially, we're processing all data in the processor at great system cost, and this is really costing us a lot. And I think this is interesting because one of the system design principles that we teach, I think in our classes, if you're teaching digital design and computer architecture, probably you're teaching balanced design, right? You say balanced design. You have to balance your design. Yes, we're preaching this to our students, but our systems immediately break that balanced design principle, right? The way we're designing our systems. It's not balanced, basically. Data is, let's say, we have this huge bottleneck between the processor and memory. Okay, and we know that this is actually a problem, but we need to do something about it more seriously, I think, going forward. So Dick Seitz, the chief architect of Alpha, he wrote this one-page article in Microprocessor Report that I would recommend that is titled, "It's the Memory Stupid," playing with the elections in the United States at the time. It was the economy stupid for some candidate, Clinton, right, at that time. So it's the memory stupid in this particular case that wins everything, let's say. So aptly titled, he said that we designed this processor, that's essentially a flagship processor of Alpha, of Digital Equipment Corporation at the time, that is capable of finishing 4 instructions per cycle. But they tested this processor and it's finishing 1 instruction every 4.7 cycles in this important database workload that we actually wanted to do well on. And why? It's waiting for memory. And basically he finishes the article with this sentence: "I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors." Only is his emphasis. Okay, and so this is to show that we have not moved much over time. 10 years later, this is my PhD thesis, my first paper actually. We basically worked with Intel to figure out what's happening in the important workloads that they're designing their processors for. And most of the time, the processor is waiting for data. The same thing, basically. Okay, 10 years after this, and this is the paper that we wrote basically with Intel. 10 years after this is data from Google, about 10 years, let's say. And Google shows essentially the same thing. Since nobody believes me or Dick Seitz, everybody believes Google, right? You can Google everything and the first result must be correct. So their paper must be correct. I'm just joking, of course, but it's a good paper actually to read. And I like the data in this paper. They basically show, according to their measurements, all of their data center workloads, these are, according to them, all of their data center workloads, most of the time they're waiting for memory. And they're doing useful work only 10 to 20% of the time. So this goes back to our carbon footprint potentially, right? This is hardware exists. It's there to tolerate this memory latency. And most of the time, it's just sitting idle. Right? So that cache that we add on top of the processor, it's going to sit idle most of the time. And we know actually more than 80%, 90% of the data that lives in the cache is dead. Dead on arrival, in fact. When it arrives, it's dead. We know that it's not going to be used. Okay, it's very interesting actually to see this. Okay, so this is a nice paper that I would recommend. So basically, there's a lot of data point to show that we have a grossly imbalanced system. As a result, we're low performance, we're energy efficient and complex at the same time. And making the processor and the accelerators even more complex doesn't help this. It hurts it actually. Because as I said, a lot of times these mechanisms don't work. So imagine a random access workload. If you have a random access workload, caching doesn't work. Prefetching, depending on the prefetching you do, probably most of the prefetching mechanisms don't work. Out-of-order execution may or may not work, depending on how much parallelism you can exploit in that random access workload. Multi-threading may or may not work again, depending on, again, how you can parallelize the memory accesses. Okay, so as a result, we have this picture. We have a very sophisticated system, and most of the time, it's bottlenecked by memory still. Okay, let's look at the energy perspective, which is actually worse. Performance perspective was bad, but energy perspective is even worse. This is data that I borrow from Bill Daly. I like the slide. I keep using it, even though it's old data. I think it's a beautiful slide that basically shows that, and you can argue with all of these numbers today because it's changed. I think the relative difference did not change, let's say, as significantly. So it's a 64-bit double precision floating point operation, 20 picojoules. A DRAM read or write, 16 nanojoules. That's 800x difference. Essentially, a memory access consumes somewhere between 2 to 3 orders of magnitude the energy of a complex addition today. Then the question is, of course, do we really want to move the data from memory to the processor to do this really energy simple operation, assuming that energy is really important for us, which is important for us? So there are multiple things to say here. I think if you want to really, of course, there are cases where you want to move that data because you have a lot of locality, but you can also do the calculation. You want to really amortize the energy cost of moving that data into the processor, and also a set of data, right? Not just one piece of data, but a set of data. How much locality should you have on that set of data so that you amortize the energy cost? It's actually interesting. Some people did these calculations. Wenmei actually had, Wenmei Hu from University of Illinois has a nice slide deck where they did this calculation. And they basically show that you need to reuse a data item by more than 2,000 times to actually overcome the data movement overhead, according to their own numbers in terms of data movement energy cost. That's a lot of requirement from our caches. As I said, more than 80% of the lines that are dead on arrival. You don't even use it once. And imagine using it 2,000 times. I will also mention another thing in this picture because it's actually nice to think about it. If you go back 70 or 80 years, this picture was different. Of course, we don't have exact energy numbers from that time, but it turns out the logic was a lot more expensive at that time. This picture came about because we've been extremely good at technology scaling. The Samos technology scaled extremely well. As a result, the transistor that makes up the computation became extremely efficient and fast. As a result, this became small. But the interconnect, which really dominates memory access, did not scale as well. As a result, its energy did not scale well. That's why we actually went back from, let's say, memory being 1 order or 2 orders of magnitude more efficient to it being 2 to 3 orders of magnitude less efficient compared to compute. It's good to think about it from that perspective also. So energy has become a lot worse over the 70, 80 years that we've been dealing with computers, let's say. And that was a complex arithmetic operation. This data is again from Bill Daly and one of his students actually. And if you want to look at a simple 32-bit addition, the relative cost compared to DRAM is even worse. That's 6400x. Okay, that's some data for you. And there are other papers that are written on this topic also that I'm not going to talk about. And as a result, we have this picture where we showed at the application level, more than 60% of the total system energy spent on data movement. And this is also growing. We didn't do a scaling study, but there are earlier papers that also tried to quantify it. This is one of the latest papers. And this fraction has been growing over time. So maybe we'll get to 99%. And this number is actually more than 90% in some really data intensive applications. So I would argue that we do not want to move data. We want to have a more data-centric view where data stays, and we want to move the data as little as possible, of course, with the overall system view in mind. Maybe we may want to move some individual pieces of data a lot, but most of the data stays somewhere. So there needs to be some more interesting calculations to be made as opposed to not having any choice. Data always goes through the processor, right? This requires us to think differently. That's why I call it a paradigm shift, because every single decision that we make today in our systems is processor-centric. In the memory controller, in the memory interleaving, everywhere, basically. Because data has to go through the processor. As a result, we've optimized the system for it. So if you want to make it more memory-centric, meaning compute where it makes sense, where data resides, then you need to change those decisions, reverse some of those decisions, and think in a different manner. So in the rest of the talk, I'm going to talk a little bit more, well, tutorial. We'll go into more into the processing inside memory. We'll talk about storage also. I like the memory part because memory is huge today. And today people design applications to fit memory, data in their in-memory database, in-memory graph processing engines, in-memory media processing, in-memory machine learning. So people try to keep the data as much as possible inside the DRAM because they know that going to storage is actually a huge cost. But of course, they cannot do it all the time, right? That's why storage is actually a big deal too. But basically, the idea is to ask memory, can you do this computation for me? And memory does the computation and returns the result. So fundamentally, this looks like an accelerator, of course. But over time, it can evolve to maybe these things being equal, right? You have distributed agents across the entire system. And they can also launch computation. Who knows, right? But initially, starting with an accelerator is easier to do. But even this accelerator has many questions, basically. How do you design the compute-capable memory and the controllers, processors and communication units, software and hardware interfaces, system software compilers and languages, and algorithms and theoretical foundations. So it's really an across-the-stack problem. And in the end, you may need to completely redesign your algorithms to fit the processing capability that's present in the memory chip. It depends on what's present in the memory chip, of course. We're going to talk about different models of this. Sometimes the processing model is very similar to what's in the CPU. That's easier, of course, right? Still, you need to consider how the data is laid out in the memory chip, how data is mapped, because today the data is mapped from the perspective of the processor, as I said, right? But if there are processors next to each bank, for example, now they don't have full view of the data. There's no processor that's central in memory. Now you need to think in a more distributed way. So I think that's the programming is still a challenge, but it's less of a challenge compared to a completely different paradigm where you do processing using memory, as we will discuss. Here, I will also mention one thing that shows how ingrained the processor-centric paradigm is in everything we do in computing. How many people have taken an algorithmic complexity class here, or teach an algorithmic complexity class? Like big O notation, big theta notation. Okay, more people are familiar with that. Maybe it's not called algorithmic complexity or theory of algorithms. But if you think about those notations, they're all compute-centric, right? We're just counting operations. But we just said, maybe that's not the important thing. Certainly, it's not at all the important thing for energy, right? If you look at it. And maybe for performance also, there needs to be something else. So I looked into this a little bit and tried to find a data-centric theory of computing, and I couldn't find much. Some people tried to do a little bit, still within the von Neumann, or I shouldn't say von Neumann, processor-centric context. Processor-centric context. So actually, we need to really develop a theory of data-centric computing as well. And if people are more theory inclined, you might actually want to look into this direction, because there's nothing in this area. You may actually do something really groundbreaking. Who knows? Okay. Okay. So do we need to take a break at some point? Okay. Oh, it's 4 o'clock. Okay, we have 20 minutes then. Okay, so I can keep going for 20 minutes. Feel free to ask questions. Okay, so everything here can be daunting, I think. And in the end, I think we'll need to rethink the stack, but maybe we can start step by step, as I said. So this is a paper that we have written for a book chapter that summarizes a lot of the research that's going on in processing in memory today with a historical perspective also. If you're interested, you can take a look at it. We're going to update this actually by the end of this month. I'm on the critical path of the updates, which is another good thing. So a lot of the things that we're not going to discuss are in the paper, but a lot of things we're going to discuss are in the paper also. There's some interesting synergy. I'm going to kind of follow this paper, but in a reverse order. We're going to talk about processing near memory, and then processing using memory, and then talk about adoption issues. We kind of talked about the earlier parts, if you will. So I'm going to argue that we need to think differently from past approaches, because in the past, people also tried to do processing especially near memory, but also somewhat using memory as well. I'm going to distinguish these two approaches first, but I'm going to also say that we need to think differently. So let's just, I think in general, there's a lot of confusion in terminology. So you may have heard processing in memory, processing, I don't know, computing in memory computing. And people actually use these terms very differently. For example, some people think computing in memory needs to be inside the chip and everything else needs to be outside the chip. I don't like any of this terminology, frankly. I have a very simple definition that is very broad, but I think it covers the fundamental aspects really well. And that's processing near memory or using memory. So what is processing near memory? It's very simple. You have memory here. You have the processor here today. It looks like they're far. You get the processor closer, 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 closer. It could be integrated into the DRAM chip, outside the DRAM chip, doesn't matter. As long as it gets closer, it's processing near memory, basically, with my definition. And I think this, basically, you keep the processor very similar to what is today, right? That's the key. It could be a CPU, it could be a GPU, it could be an FPGA, it could be any type of accelerator you can design, except it's just closer to memory. Closer may mean near bank, just like Samsung and Hynix are doing, for example. It could mean in the logic layer of a 3D stack. It could mean something in a monolithic 3D technology. So fundamentally, it's very similar to what we do today. We program this processor very similarly to how we program whatever processor you have today or accelerator you have today. It's just closer to memory. Okay, processing using memory is, I think, fundamentally different. And the idea here is you don't have the processor. Processor doesn't exist. What you do is you start with memory, and this is a memory device. Normally, we think of a memory device as you just store data, right? Load, store data. Okay, it can do it. It's going to still do it. But it's also, you realize that it also has some capability to do computation. And I believe any memory device has also some capability to do computation, the way it's designed. We will see examples of DRAM later. People have shown examples of flash memory, for example, or STT-MRAM, et cetera, PCM, emerging memory technologies. You basically realize that there's some fundamental computational capability in memory cells and the logic and the existing logic surrounding memory. And you harness that to do computation, usually bitwise, some sort of bitwise computation. Now, this is a different way of thinking, clearly, right? We don't normally design our programs this way. We basically have a processor that executes stuff or accelerator that executes stuff. Processing using memory is going to be completely different. That's why it's going to be longer term, in my opinion. That's why all of the prototypes of processing in memory is processing near memory today. Right. Processing using memory needs more work into the future, both from the technology perspective, because you need to make it reliable, at least in most applications. And you also need to make it programmable, easier to program. And that's a much more difficult task than in processing near memory. Yes, please. Okay, go ahead. Sure, I'm waiting. I'm happy to update the terminology. I would say that's processing near memory. Because you're adding an additional computation unit, right? There could be hybrids where you do processing using memory and near memory, and that's certainly possible, right? But what you're doing is adding additional accelerator, some sort of accelerator, right? It's fine. This distinction is not about programming. This distinction about whether you place some logic near memory or not. So I think the distinction is, yeah, exactly. But the processing is logic, yes, in my view. You could actually, okay, maybe you replace processing using logic. Logic using memory, logic near memory, and then you have logic in memory, which is what people have started with in 1960s. So absolutely, I like that also. No question about that. Okay, this is a fun discussion. Now you get rid of all of the, let's say, lack of clarity, computing in memory versus computing. yeah, anyway. Because people say, it's very confusing, I think. Sometimes people distinguish between processing in memory and computing in memory, and I get a bit crazy with that. I don't understand that distinction. Okay, anyway, let's talk about these two PIM approaches. So overall, it's processing in memory, right? And the mindset in these initial approaches are at least similar. Memory is an accelerator. And this is the concept that we know. We're able to build a lot of accelerators on the, let's say, left side of the memory bus, right? And we do a great job with a lot of them, actually. But the downside is all of them are bottlenecked by memory. Why don't we actually put some accelerators on the memory side? Whether they're processing using memory or processing near memory, we will see some examples of this. And programming may be similar to a conventional accelerator in the end. We'll talk about that later on, I think. But let me give you some examples to begin with. I'm not going to go into a lot of detail, but we can certainly talk about details if you want. And some of these are relatively old, but there's new work that built on these works. Well, this work at least. I think once you start thinking of processor memory as an accelerator, then the question, of course, becomes, what do you accelerate over there, right? And I think having a whole system point of view, what kind of applications should you accelerate is important. And this is some of the early work that we did on graph analytics. I think graph analytics is really important, actually. Clearly, people are doing it, and there are many users. This is a good fit for processing near memory also because it doesn't scale very well as you add cores to it. Here you can see an example where we quadrupled the cores and you get only 40% performance improvement. And the reason is there are a lot of parts of a graph analytics workload where you have frequent random memory access and little amount of computation. Of course, it depends on what you're doing on the graph, but many interesting workloads have this characteristic. So your processors are heavily bottlenecked by memory. So when we started doing this work, we wanted to look at accelerating graph processing using 3D stacked cubes. I'm going to call these cubes. You have logic layer, memory layer. They're connected through silicon vias. At the time, hybrid memory cube was quite interesting. When we started, it was like 2012 or so. In the end, the paper was published in 2015. So it takes some time. It was rejected multiple times, but that's a different question. Essentially, we wanted to use these cubes, but high bandwidth memory can be also used for this purpose. And I think this is even better with three-dimensional technologies. So we're going to add some logic so that we can do some graph processing underneath these memory layers. And the idea is that we're not going to move the data. We're going to ship the computation to the data such that the updates to the graph nodes are made without moving the graph nodes. Yes.
Usually they say that when you talk about a logic die over there, it's the base die at all. I think add additional logic die or
yeah, that's a good question. I mean, it depends on how you design and optimize the base die, probably. If you don't want to put computation, you may actually optimize it for 5 only. That would be my guess. But I think if you want to design the base die for computation, we looked at a lot of data and analysis. You can put some computation in there. You cannot use the entire base die for computation, no question about that. But there's some area where you can do some amount of computation. And we put in-order cores, so simple in-order cores in this particular case. Yeah, we're not using the entire base die area. But I think, I mean, I know what you're talking about, I think. I mean, my feeling is that, yeah, you could optimize the base die. Yeah. Yeah, sure. But maybe you add another base die at that point, right? Sure. Yeah. That's why I think monolithic 3D technologies are even more interesting. You have a lot more space in those dies, right? Okay, so basically the idea is to start with this cube And in the cube, you divide the cube. It's already divided into actually what's called vaults. And these vaults have memory controllers in them, DRAM controllers. We just put in-order cores, simple in-order cores that don't occupy a lot of area into each vault. And as I gave you the idea, you to scale up, you have many of these cubes because your graph may be huge, of course, right? And you partition your graph across these cubes, and then within the cube across vaults. And you don't move the graph nodes that you're updating, but you move the intermediate data and the computation that you need to do to update the graph nodes. That's essentially the idea. So you program it using very similar to remote procedure calls, remote function calls, very similar to how a lot of distributed systems are programmed today. Graph partitioning is important because you don't want to move the computation between the nodes, the computation and the intermediate values, I should say, between the cubes, even between the vaults, but within the base die, it's not as important, let's say. But if you go through the cubes, then it's essentially external accesses. So later work than our work actually improved this graph partitioning aspects, for example, a lot to improve the performance beyond what we have gotten. So that's the idea essentially. If you look at this, you offload your graph computation onto this accelerator. It's like a primitive GPU. It has non-cacheable, meaning there's no cache coherence between the processor and what this graph processing unit is doing. And it's physically addressed, meaning there's no virtual memory over here. So this is really a primitive GPU. And GPUs were maybe 25 years ago like this, 20 years ago also like this. So over time, maybe things can change for these accelerators as well. Okay, I don't want to go into a lot of detail in this because there's a full system design paper. It's in simulation because we don't have the chips at the time, but that's the idea. And I'll focus on the results. So if you look at the systems that we compared at the time, these are the best systems, hybrid memory cube, and the memory bandwidth was 640 gigabytes per second. And Tesseract doesn't look like any of those systems. We call this Tesseract because memory and processing is coupled basically. And you basically scale the system by scaling both memory and the processing, where it's a lot more difficult to do in this sort of systems, including chiplet-based systems, I would argue. Yeah. And the memory bandwidth that is available to the same number of cores compared to the baseline is very high, as you can see over here. And these numbers have changed over time. These numbers all have increased essentially. We did the evaluations, as I said, on 5 graph processing algorithms. And on average, you get more than 13x performance improvement with this sort of system. And again, we didn't optimize the system a lot. Later works, there are actually many works published on this topic that have improved what we have done. Some of them, for example, improve load balancing. Some of them improve graph partitioning. Some of them improve interrupt handling, data mapping, etc. It's very fascinating to see. And I think this number is much closer to 100x right now, even higher than 100x in some of the public publications. And energy improvements are also similar. We showed initially that the energy improved by 8x. But recent work that improved all of these other aspects that I mentioned showed that energy improvements are actually closer to 100x or even more. So I think this is one example. I wanted to show this example early because it also shows the example of how important optimizing, sorry, maybe this is the time to take a break, you know, optimizing a data-centric system is. We didn't start with the most optimal system, but over time, other people built on the system and they showed that you could get even higher improvements, 100x. And again, this is not a trade-off. You get 100x performance improvement with the latest and greatest improvements, and 100x energy reduction. So that's at the same time. I think we should be shooting for those directions. Okay. Should I cover this work or should we take a break? Let's have a break. Okay, let's have a break. I don't know when we come back. 20 minutes, okay. As long as there's coffee up there, I guess. Okay. Okay, let's have a break and we will continue. Thanks. Hopefully there will be more questions after this. We're going slowly, but it's good. Yeah, exactly. It's good to have people asking questions. Yeah, absolutely. I'll pause the recording. Okay, good. Oh, no, not live on YouTube. There you go. Okay. Okay, now that I have my coffee back, it's going to be easier. Oh, some people still coming in. I don't know. Okay, so let's get started. So we looked at one case study of accelerating graph analytics using processing near memory. I'm going to give you another case study just to show you that it doesn't need to be that hard. So I think the previous one we saw was a bit harder because you need to change the entire system, rely on an emerging memory technology. But I think there are some things we can do that is relatively simple. Maybe it's not with immediate existing hardware, but relatively simple changes to hardware. And that's genomic data filtering. This was published actually very recently at S+ this year. If you want to learn more, you can look at the paper. I'm going to give you a very high-level overview. And I think the overview is, today we have a lot of accelerators or CPUs for genome sequence analysis. And a lot of the genomic data actually gets stored in the storage system and moves all the way into the computation units over here. So remember the cost going to main memory in terms of energy and performance, it was high, but going to the storage is even higher. And Georgi earlier was saying that you should really have talked about going to the network, right? Once you go to the network, to the internet, those energy costs are actually even higher, basically unimaginable. And I think that's a good idea. It's good to get some numbers related to that. But storage, we have numbers. It will be reflected in the results, but you can read the paper for more as well. So basically, a lot of genome sequence analysis applications do computation, which is alignment, sequence alignment. And there's a lot of computation overhead for this, but there's a lot of data movement overhead for it as well, especially if you're doing very large scale genomic analysis, doing a lot of comparisons to understand, for example, different variants of a species. So people have targeted the computation problem a lot, actually. There's a lot of research on heuristics, software-based heuristics, accelerators, and filtering mechanisms so that the computation doesn't become huge. And the paper referenced a lot of papers. I actually referenced some things earlier in the talk. So the computation overhead has reduced a lot over, let's say, 1 decade or so. This made data movement even worse of a bottleneck, basically. Your computation is a lot more bottlenecked by data movement today. So we still have the data movement bottleneck. Whatever heuristics you employed over here, they reduced the computation part. So data movement remained the same. So it's a bigger bottleneck right now. And in this work, we wanted to look at the storage system as a data movement bottleneck. And basically, if you think of it that way, the idea is do some filtering in the storage system such that you minimize the data movement that goes to the computation unit. Basically, do the simple operation on the storage system, leave the complicated operations to the computation unit or the accelerator over here. That's the idea. We'll go into just a little bit more detail. What are those simple operations, basically? Usually, those are filtering operations. So if you can, for example, in the storage system, figure out that some comparisons that you're going to do, some alignments you're going to do are going to be exactly matching, then the computation unit doesn't need to do that. So usually in genomic data analysis, you want to compare a sequence, let's say 100 character fragment of a DNA to another 100 character fragment of another DNA, let's say. You try to match. Exact match comparisons are easy. You basically compare each character in parallel and you're done with it. If it's an exact match, you get an exact match. If it's not an exact match, you say basically, no, it's not an exact match. So that's a very simple logic to implement in the storage system. But normally the answer you're looking for is not just exact matches, right? What you're really looking for is how close are these 200 base pair, 100 character sequences to each other. You really want to identify where do they exactly differ, how much do they differ, and what kind of differences are there? Is there an insertion in one place? Is there a deletion in one place? Is there a mismatch? Because they're all indications of potential It could be whatever you're looking for. It could be diseases, for example, different kind of variants, etc. So the edit distance computation, the alignment computation is actually a really expensive part. And the idea here is to actually do the tough computations in the computation unit accelerators that are designed for it, and leave the easy parts to the storage system, so that simple computation can be added to the storage system in a very easy manner. And that's the idea. And the hope is that you're filtering a lot of the reads. It's called reads. This has terminology in genome sequencing. These are basically fragments of DNA. And most of the data stays in the storage system, and only the tough parts go to the computation unit. And there are two types of reads that we found in this particular work, at least, that are good candidates for the storage system to compute on. One is exactly matching ones, meaning, as I said, the exact match computation is very easy. So add some very simple logic to figure out whether the two reads you're comparing are actually exact matches. And if they're exact matches, that's great. You're done. You don't need to send anything to the computation unit except for marking something saying that, oh, these reads matched. So there needs to be some metadata communication clearly. And the other part is completely non-matching reads, meaning this requires a little bit more understanding. So I'm not going to go into it in a lot more detail, but there is a way to also determine whether this 100 character sequence is definitely not going to match this other 100 character sequence within a reasonable threshold that you're looking for. Usually when you do these comparisons, you have a threshold. Threshold could be 5%. Basically over 5% difference between two strings of characters is not something what I'm looking for, because that's too much difference between these two different potential species, for example. That number could be 10% also, depending on the analysis you're going to do. So basically, there are ways of figuring out whether two of these sequences are not going to match each other within that reasonable threshold. And that logic is also relatively simple, more complicated than exact match logic, but it could be integrated into the storage system. So identifying these functions that can be more easily integrated into the memory or storage system and doing them near the storage devices can actually buy you a lot of performance space. That's the takeaway. And this is an example case study in genome analysis. And that's the idea of GenStore, basically. And this targets both computation overhead and data movement overhead in the end. I'm not going to go into more detail, unfortunately. Otherwise, we have to go into a lot more things here. But we found out that you can get, again, significant speed ups and energy reduction at the same time at very low cost, very simple changes to the logic, hardware logic in a storage system. And the key difficulty actually here is figuring out what computation should be done over there, and also enabling it in an existing SSD, for example, solid state drive, without changing or asking too much from the designers of the SSD to make changes. And that's the paper. There's a lot more detail in the paper. Any questions? Yes, please. Sure. This one? You mean exactly matching versus non-matching? No.
Everything that reaches the threshold to send out, but how do you know that they will look exactly match?
Okay, we're talking about, let's say, 100 base pairs, right? 100 characters. You're comparing to 100 characters. There are two types of logic. One is exactly matching logic circuitry, and the other is non-matching. If the exactly matching says it's exactly matching, then you basically send out saying that it's exactly matching.
So you do all of them in parallel.
Yes, that's right. That's right. Yeah, sure. Yeah, maybe there's a way to do it sequentially by merging the logic, but we didn't do that in this particular case. Sure. Okay. Okay. Any other questions? Yeah, I think this is so compared to, for example, the earlier idea we discussed in graph analytics, this is a much simpler system, right? This doesn't change any of the existing programming paradigms. It just enables the storage system to do some more computation. Of course, you need to change your application a little bit so that the metadata communication between storage and computation units are done correctly, right? Yes.
How is the data stored in our system? Does it come from the distribute it to those?
So initially, all of the data is in the storage system, basically. So you gather some genomic data from the nanopore device that we have seen at the beginning of the presentation, and that gets stored in your computer. And then you say, oh, okay, I want to now do some analysis on this. And then the CPU pulls in from the storage system. In a traditional system, CPU pulls in everything and back and forth potentially, right? But here, the storage system is slightly intelligent, let's say. It does some filtering so that CPU doesn't, data doesn't move a lot. Exactly, inside the storage system, basically. Exactly, overhead of basically getting the data out of the storage system, everything. So that's a lot of actually overhead. So potentially, yes, that depends on the use case, right? That's what I was talking about earlier. So you have this nanopore device and then you connect it to a computer and store the data over there. Depending on the use case, you can do some online processing inside the nanopore device or while the data is moving so that you don't store everything, right? Depending on your goal in the end. Yes?
So just wondering why the acceleration factor is so high. Do you do all the filtering in a parallel way? Because I just imagine having this parallel, this matching mainly in the storage controller, the C controller, just before you would send the data out, but then it wouldn't gain any speed up because it just would not transfer the data, but you have to read it from the flash memory to compare it. So is the comparison logic really distributed into the flash memory, or how should I manage?
Yeah, so certainly it's distributed across all of the flash chips. So if you look at the paper, you have distributed processing across the flash chips.
Okay.
Yeah.
So this is how you get speed up.
Yeah, you do a lot of things in parallel, basically. No question about that.
One end of the cable, another end of the
Yeah, exactly. That. Yeah, I mean, you still gain speed up because you free the CPU to do computations that are hard, and you have more bandwidth in the CPU to do that, right? Also, you improve locality in your caches, etc. So you would still gain speed up, but not as much speed up. Okay, great. A lot of questions. Okay, let's move on. So I intend to give some examples of these from our studies. And I think I'm going to talk about this one a bit. This is the paper that I mentioned where we analyzed these 4 workloads from Google. Our goal was basically to understand multiple things. One is the impact of data movement in mobile devices, and also a potential way of alleviating the data movement bottlenecks. And we wanted to focus on these 4 workloads because we had a lot of internal support from Google for these workloads. Clearly, versions of these workloads exist for other, let's say, companies or cell phone environments. And we already discussed this, right? We found out that a lot of the system energy is spent on data movement, and we wanted to reduce the overhead of data movement by moving computation close to data, again, in a 3D stacked DRAM system. And the challenge, again, is limited area and energy budget, and the paper has a lot of discussion on that energy budget, as limited area budget and energy budget, as we discussed earlier. But the other observation is very similar to what we discussed just now. Data movement often comes from very simple functions, or there are some simple functions that are actually a very good fit for processing near memory. And essentially, putting logic near memory for these functions is not a lot of overhead. And also it buys you a lot of benefits. That's the idea. Identifying these functions is actually really important. We hand identified these functions in this particular case, but later we may talk about at least not a fully automated, but somewhat semi-automated methodology to identify these functions that would benefit from processing near memory. And once you identify those functions, they can be processed in a small low power core or small fixed function accelerators, or maybe some reconfigurable logic as well. If you don't want to have the cost of a lot of accelerators, for example. And for example, some functions are compression, decompression, which is employed heavily in video encoding and decoding. Motion estimation was another one that we offloaded, actually, that had a lot of data movement overhead. Actually, compression and decompression was also quite heavily employed for tab switching in Chrome web browser, for example. When you switch tabs, some idle tabs get automatically compressed so that you don't waste a lot of memory space. And then they get decompressed when the user switches back to that tab. So that is actually a frequently data movement causing function. And overall, in this work, we observed, of course, the environment is a bit different, but the performance improvements were, performance energy improvements were 2.2x and 2.3x compared to the baseline system. So it's quite substantial still, but maybe not as much as what we have discussed earlier, right? Because here we're moving individual functions and maybe we're not identifying all of the functions because it's a complicated workload. We're not moving the entire workload to the memory. We're just moving individual functions. But this reduces a lot of the overhead of processing in memory also, in my opinion, shipping individual functions. Okay, another example is, for example, in inference, machine learning inference. When you go from layer to layer, you change data formats sometimes, packing, unpacking, and you do quantization in machine learning. So these actually cause a lot of data movement. And these were the two functions that we targeted. And they're very simple functions also to implement near memory. So here you can see that you can specialize somewhat your near memory logic to the applications at hand. Any questions? Yes, please.
How sustainable are these functions? Because are they like the same or long time scale? Because it's always the screen store and the graph processing. They all target an application. Some do the same, people do other stuff. And these simple functions can change, like you mentioned. Are they like the same? Because it feels like they are target one application and then the application changes because someone develops something new and throw out.
Well, in this case, we look at in-order cores also. So simple cores can actually do these functions also because they're very simple functions.
Basic, simple core can be programmed.
Exactly. So it's you need to have some programmability. Even if you have a fixed function accelerator, I think you should have some sort of programmability to cover, let's say, a family of functions as opposed to just that function itself, right? Yes. But I think I like reconfigurable logic a lot because you can actually update a lot of that. But for example, in the Tesseract work, it was all in order cores. There was nothing specialized for graph processing. Later works, maybe some of them specialized for graph processing, but not all of them. Yes, please.
You mentioned in one of your previous slides, something about simple functions.
Yeah.
What simple function you have in mind? I mean, compression is not simple function. It's computationally intensive. So could you say some more words? Yeah.
I think like this one is some of the simplest ones, right? The unpacking and unpacking of data. These are simple compared to compression. The compression, they're simpler, right? Quantization is also simple. You're chopping some bits, right? You're deciding. It's essentially conversion of data from one format to another format. I think I agree. Compression and decompression are not simple compared to these, but they're simple from the grand application perspective, right? They're much more complex functions that an application also executes, and you can bound these compression and decompression functions.
Yeah, I was asking you because I mean, if you have a rule, let's say what simple function, in order to identify, let's say which data moves which function will execute in memory. I mean, the designer will decide what is simple.
In this current case, in this case, yes. But I think going forward, yes, I think what you suggest. I don't know if there's any work. I don't think of there. I cannot think of any work that does what you suggest right now. I think it's a good direction for research for sure. No question about that. Somehow you figure out this function. Not only just you figure out this function would benefit in terms of energy and performance, but also figure out whether this function, what kind of area and what kind of energy and what kind of power would it consume if you
can find automatically what is simple function in the runtime. I mean,
it makes sense. Well, these are good areas of future work if people are looking for future work directions. There's a lot in this direction. Okay, one more question. Yes.
How do you monitor the workloads? Did you use like did you just check the number of calls to the OS APIs memory functions or
like how did we monitor this to figure out which functions are causing a lot of data moments, etc., or energy?
Yes.
Yeah. So we did some real device measurements plus some modeling of the energy usage of different functions. The paper has a lot more detail on the terminology, but it's a function of a real device measurement. In fact, I think some of this is really open source on the Chromium, at least for the Chrome browser part. I should speak of the Chrome browser part. The Chromium webpage, they have some telemetry mechanisms where you can figure out like what functions are causing trouble for you, let's say. Energy modeling is, you need to model that a little bit more. Does that answer your question? Yeah, okay. Okay, let's move on to, well, I'm not going to give you other examples because we don't have a lot of time for a lot of examples, but there are actually a lot of other examples. I think GPUs are another possibility where today's GPUs are huge machines clearly, but there's potential for reducing the data movement in GPU by having simple GPUs in the logic layer, for example, so that you can do the, let's say, not so heavy functions again in the logic layer and minimize the data movement across the entire system in a system that looks like this. And if you're interested, you can take a look at some of the papers. In this paper, we also wanted to do it completely transparently. So basically, someone writes a GPU application, and at the compiler level, you completely transparently decide where this function executes, in the main GPU or in the logic layer. And that's a difficult task, I think. I think it's good to look into this, but the performance benefits usually become much lower once you try to do it completely transparently. It's a lot easier if a smart programmer figures out how to do it, let's say. Maybe I shouldn't say easier, but it's a lot better in terms of performance and energy benefits. So if you look at this paper, the performance energy benefits we get are on the order of 30 to 50%, not 2x or more. Okay, so I'm not going to cover a lot of these other things, but I think linked data structures are actually quite interesting to look at, like offloading some linked data structure computation to the logic layer, where we do that over here. That has a lot of possibilities, dependent cache misses. So there are a lot of interesting things. I already mentioned the client modeling part in an earlier paper. I'm not going to talk about that. So there are a lot of case studies, basically, of real applications. And these are just our case studies. There's also a lot of other case studies in the literature that I'm not covering clearly here. Okay, I think time series analysis is also another interesting application. This is actually another application that's used by many people in the world. Astronomers, for example, you're getting a lot of data in a series and you're trying to analyze it online or offline. We see a lot of benefits in terms of accelerating time series analysis in near memory, using specialized accelerators or CPUs or GPUs near memory again. Okay, there's more, but maybe we should move on. So the point of all of these is really, there are a lot of applications. If you know what you're doing, let's say, there are a lot of applications that could benefit from processing near memory. And in some cases, you really need to know what you're doing. Let me put it that way. It's not the programmer, in this particular case, we looked at hybrid transactional analytical databases. And my student really spent 3 years to really understand how these databases operate. And the paper was published after 3 years of hard work, let's say. And the idea is you partition, you have two different accelerators for two different types of queries, analytical versus transactional. And the design of them are completely different. So it's really across the stack design. This particular case, for example, is an across the stack design. You design the algorithms to match the processor that you design also. Processor can be a near data processor also, right? Okay, yes, please.
For the database, okay, since I have started recently to work with databases and exploring the correlation between stain memory, okay, and the database, okay. So here, what kind of memory do you have? I mean, classical DRAM system?
Yeah, this is classical DRAM system, yes. Yeah. For the processing in memory system, we have a hybrid high bandwidth memory. Okay. Yeah. Yeah. Okay, that answered your question. Yeah, sure. Okay. Okay. Yeah, I will refer people to these papers because there's no way I'm going to cover these papers in 4 hours also. If people are interested, I think. I find it fascinating, I think. I will cover this one a little bit because I think this is quite interesting also. this also brings together some other points that I was making earlier. Unfortunately, I don't have a lot of slides on this, but this is another study that we did with Google. After doing the study of understanding their mobile workloads that I discussed, we also wanted to look at neural network models, especially on edge devices, mobile devices, basically. And this is a like quick summary of the work. Let me cover this relatively quickly. But basically, we analyzed 24 edge machine learning models that Google uses. Unfortunately, these are proprietary. They didn't let us, let's say, open source it since they use it in their commercial works. But they allowed us to actually analyze the state-of-the-art edge machine learning accelerator that they employ, which is the Google Edge TPU. And we wanted to basically develop an understanding of how good this accelerator is for these models that it is kind of designed for. I mean, not complete designed for, because it's still a general purpose accelerator. It's a neural network, general purpose neural network accelerator, but it's still designed for neural networks, right? And we found out that basically, this is a monolithic design, basically, single accelerator, systolic array-based accelerator that's designed specifically for neural networks. A lot of computation capability, but it turns out it doesn't, most of the time it's idle, especially in more sophisticated models like LSTMs. So basically the same story that we discussed earlier applies to accelerators as well, right? Most of the time this accelerator is idle because it's waiting for memory, even though it has a lot of memory, by the way. The results, the numbers are really in the paper. I don't really have the slides over here. And it's also very energy inefficient for the same time because of the way it handles memory access again. And the key issue is that it's a monolithic design and it doesn't have any data-centric properties. It doesn't account for different properties of layers that we're going to look at actually in a little bit. So the idea over here in this work is to have a heterogeneous set of accelerators. Some of them are one of them is compute-centric, just like this accelerator, but a smaller one, much smaller one. And two other data-centric accelerators that are near memory to minimize the data movement overheads, and also somewhat customized data flows for some of these layers. That's the idea. So there are multiple things going on. One is compute-centric, one accelerator that's compute-centric, two accelerators that are data-centric, and the two of the accelerators have different kind of data flows. The goal is to cater for the properties that we see in these different machine learning models. And in the end, you get more than 3x energy and performance improvements. And also, combined together, these three accelerators are smaller than the single monolithic accelerator that was built. So that's the interesting part. You have three accelerators. You have a little bit more design complexity, of course, but three accelerators together provide higher performance, higher energy, and lower area. So I think this, if you kind of consider data-centric design and also optimizing the data flows in these neural networks, you can get there, in my opinion. So let me give you a little bit more detail. So we basically analyzed these different neural networks, state of the art at the time at Google. And these are some examples of what we found. The paper has a lot more, but we found a lot of diversity across different models. For example, this graph is showing the parameter footprint. And this this axis is showing the flop per byte, arithmetic intensity, essentially. And there's a huge variation across the different models. And layers, neural network layers from long short-term memories and transducers tend to be on this side. Basically, they have very low arithmetic intensity, as you can see, but they have a huge parameter footprint. Now you can say that perhaps it's a very good fit for processing near memory, right? You're not doing a lot of computation, but you have a lot of data. And maybe this is not a good fit for processing in memory if you're up high here, right? Okay, so the paper has a lot more graphs like this. And also there's a diversity even within the models. Within each model, while you're executing different layers, you see different arithmetic multiply and accumulate operations in terms of, these are absolute numbers over here, but also different arithmetic intensities over here. And even within a model, variation can be up to 200x across different neural network layers. And variation arithmetic intensity, according to what we found, can be like 240x, as you can see over here. So there's a huge variation, basically. And the key is that a monolithic accelerator cannot take into account that variation. It's just monolithic. It's designed with a single, let's say, simple systolic array. That's it, and it's processor-centric. Right? So basically, this is the HTPU accelerator. It at the high level, you can look at it this way, right? You have some buffer, some network on chip, and some systolic array. And it basically takes in all the models. We basically replace it with 3 accelerators. In this particular case, 3 accelerators, but the idea can be expanded to more families, of course. One is a compute-centric accelerator that's much smaller. It's very similar to this, but it's much smaller. And the other 2 are data-centric accelerators. Unfortunately, this picture doesn't do justice to them, sorry. The other 2 are data-centric accelerators where the data flows are optimized based on the families of layers. I have another picture. I used to have another picture where we show the families, but unfortunately, it's not in these slides. And the idea is to have a software runtime that identifies the layer characteristics that you want to execute and schedules the layer that's appropriate to different types of families of layers to that accelerator. And that schedule is also important, clear. So there's more complexity. So the trade-off is there's more complexity in the system, clearly. There's a runtime schedule that needs to make a decision as to which accelerator should execute which particular layer you're encountering. And this can be optimized further by actually somehow co-designing these accelerators as well. We do not do that as much, but like the scheduling algorithm can also be improved significantly. Okay, that's all I have over here. Yes, please.
Runtime engine is a kind of orchestrator. I mean, orchestrate which task from the above models will decide which
accelerator.
It's a kind of orchestrator. Actually.
Yes, yes, you can think of it that way. It's a scheduler orchestrator. Yes, sure, sure.
I mean, for me, orchestrator is more generic than.
Sure, sure. Yeah, yeah, exactly, exactly. Yeah, exactly, because you can really co-schedule and all of that stuff.
And the underlying hardware is actually the same for all.
No. Unfortunately, this picture doesn't do justice to it. yeah. I don't know if I have any other picture in this set of slides, but let me see.
So sorry, because.
Yeah. If I search for Menza, will I be able to find any backup slides? I can try to pull up some backup slides, but. Yeah, each of the accelerators are basically, these are 3 different accelerators. Yeah.
And the underlying hardware is different.
Yeah, completely different. So for example, okay, I don't have slides, but I mean, the general characteristics is, so this accelerator has a lot more computation. It is a larger systolic array. It's still smaller than this one, for example. It has reasonably large parameter caches, for example. But this one has a much smaller systolic array on the memory side. Does that make sense?
Yeah.
And the other one has some other characteristics. Yeah.
Sorry, I would like to emphasize. Now we're working with use TPU, the proof of concept of using TPU for satellites.
Okay.
The European Space Agency.
Okay, interesting.
Are looking at different TPUs, and since
okay.
It's closed system. We try to make a reverse engineer what's behind.
Oh, okay, I see. Yeah, sure. Yeah, so, sure. No, it's not secrets. Basically, we write. Yeah. Of course, we cannot share secrets, but everything we can share is in the paper. Actually, the paper describes the baseline HTPU that we use, and of course, more freely describes what we use, what we design. Yeah. But I cannot claim that the current TPU that Google is using is the same as what we described. Yes.
Why the partitioning of the accelerators?
Yeah.
Which layer to deploy which accelerator? Why you do it runtime? I think you can do it offline. I mean, you know it's layer.
Yeah.
So is it something that you can do offline?
I mean, partially you can do offline. That's a very good question, basically. We didn't explore the huge design space for this. Maybe there's more. I think there's room for future work in this area. I think partly it can be done statically, but it's also a resource allocation problem, right? It's not just you know what's going to be executing everywhere. You may have many more inference tasks coming in than you have anticipated. So if one is not available, if you're let's say ideal accelerator is not available, this runtime schedule needs to make a decision as to which one should it use, right? That's one of the reasons. But I think it's good to perhaps explore whether the layer characteristics change. And I think they do change somewhat depending on the type of inference task you're doing. So that's something that needs to be looked at more, let's say. Exactly, it's the task.
It's the same network.
Yeah, yeah, exactly, exactly. Mm-hmm. Yes, please.
So like a task would be like 3 sequences in parallel, and then when one arrives, overlaps with the others, one after each other, maximize the density of the work.
Could you say it again? I couldn't hear very well. It was.
No, on this side, I was thinking this kind of accelerator, you could use it to, to like do more than one single inference model at a
Yes.
time with runtime. So you, for example, have 3 models that inference and somehow they overlap during the computation and build the workflow with this.
Yeah, yeah, exactly. I mean, we didn't do that in this particular work, so you can certainly exploit that parallelism as well. Yes, I think this sort of accelerator is very good at that. We didn't, as I said, our scheduler is very basic at this point, but you can certainly do that. Mm-hmm. Yeah, yeah, exactly.
Use a wide array.
Mm-hmm.
So you can, for example, to deploy like 3 models that run parallel. You might have that one task of the one page or the other one.
Yeah. Yeah, 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 certainly. I think that people can certainly pick up on ideas like this. Yeah. Yeah. I think, yeah, certainly that is another direction in terms of flexibility of the accelerator fabric, right? Right now, it's not very flexible. This runtime enables more flexibility in terms of what runs on the accelerator fabric. Yeah. Yeah, I know there's a lot more to do in this area for sure. It's a very ripe area. Okay. For exploration. Okay, maybe we should continue. I already mentioned this, so I'm not going to talk about it again. I think this is also fascinating. But these are all examples, I think, that we will need to start revisiting the entire stack, perhaps on a case-by-case basis with applications. I believe we can get there step by step too. So I think all of these are really good case studies where near memory computing can help a lot. Okay. So there are open problems also. Maybe we should discuss that after we discuss the. I'll discuss some more open problems. You can find more of these, but let's discuss the other approach to processing in memory, which is processing using memory now. So we're going to switch gears and not talk about putting the processor closer and closer and closer to memory, but we're going to talk about processing using memory. Any questions before that? Okay. Yeah. So the idea, if you recall, was to use the operational principles of memory to perform essentially computation. I'm going to add bulk data moment because existing memory chips actually can do data moment very nicely also. And we're not allowing them to do it today. But data moments are consuming a lot of our energy and performance as we had discussed. So you can, for example, exploit the existing internal connectivity to move data between different memory banks, for example. You can exploit the analog computation capability that exists in essentially all kinds of memory. Maybe this is at least all kinds of memory that I am exposed to, let's say. And who knows what else. You can certainly add more internal connectivity to help this and add more, let's say, aids to help this computation capability, right? Of course, you can put logic on top of this as well, right? Just like we discussed, but that is not pure processing using memory from my perspective, as we discussed earlier. In the purest sense of the term, processing using memory exploits whatever exists. Okay, maybe I shouldn't say whatever exists. The operational properties that already exist in the memory cell in the device. Okay, so I'm going to give you some examples. I'll start with cheating. It's not going to be computation. It's going to be data copy and initialization. And many applications do data copy and initialization, sometimes at large scale. For example, operating systems initialize pages for security purposes, privacy purposes. You do checkpointing. Whenever you fork a process, you do copy on write. And that could be a lot of copies that you make. And imagine you're initializing a 1 terabyte database. That's a lot of writes that you do to memory. And today, everything goes through the processor, basically. If you want to do some sort of copy or some sort of initialization, you have to bring the data that you're copying and the destination to the processor and then write the data back to memory. Even with initialization, everything needs to go through the caches, right? Okay, so there's some interesting data point over here. Like after we published our original paper on this topic, Google folks in this earlier paper that I mentioned from Google published their own paper and said that only two function calls, memmove and memcopy, in their data centers occupy 5% of the execution cycles across all of their workloads. That's actually fascinating, I think, for two functions only. And they said that approaches like what I'm going to describe are going to be more important into the future partially because of this, let's say. It's interesting that our paper was initially rejected, actually, saying that what fraction of the operations are this? So it was good to see this paper from Google 2 years later answering the reviewer's question that we couldn't really answer completely, let's say, because we can only know our workloads, right? And they exist, yes, according to our workloads. Okay, so basically, as I said, if you want to copy a source page, white page, to a gray page over here, today you have to go through the processor, right? You need to bring the data, or at least through the memory controller. You could offload to the DMA engine, actually, in today's systems. But you bring the source page byte by byte into the L1 cache. You bring the destination page byte by byte, do the write, and then write back the data. So that's a lot of moves, data copy. It could be a small page, like 4 kilobytes. Still, it's occupying the data bus. So the idea is very simple here. Let the memory do it and don't disturb anything else in the system. And that's the idea, basically. Data doesn't move outside of the memory chip in this particular case. And clearly, this is low latency because you don't exercise the long interconnects, and there's low latency data movement interconnects inside the memory. Low bandwidth utilization, you don't actually move any of the data unless you need it after some point. And there's no cache pollution that's caused in the caches, so your caches can be preserved for something more essential. And no unwanted data movement on the memory bus. So at the time, this number didn't change that much, by the way, because memory latencies are not reducing that much compared to, like, let's say, in the last 10 years. In fact, in some cases, they're increasing today because memory latency, unfortunately, is not the primary concern of DRAM manufacturers. They're usually improving bandwidth and capacity, but not latency, basically. Partly because latency is hard to improve, but partly because it's a conscious choice that they made because latency is costly to improve compared to the other ones. So if you want to do this 4 kilobyte page copy from one page to another page, it takes about 1,000 nanoseconds and 3.6 microjoules in DDR3 and very similar amounts in DDR5, let's say. So if you want to do this copy inside DRAM with the method that we're going to discuss, it reduces the latency and energy significantly, 90 nanoseconds and 0.04 microjoules. So that's quite significant. And the idea is actually very simple. The idea is called row clone. It's quite old by now, but it's a nice idea, I think. You basically assume that source and destination rows are in the same subarray, DRAM subarray. You first activate the source row. When you activate the source row, that brings the data into the row buffer, the sense amplifiers in the row buffer. Now you have the data very strong in the sense amplifiers. That's the goal of the sense amplifiers, right? And amplify the weak signal that you have in each cell to a strong signal. And the second step is to activate the destination row where you're going to copy this data into, which disconnects the source row from the sense amplifiers and connect the sense amplifiers to the destination row. Now, if you do that, you just use the sense amplifiers as a temporary buffer to copy data from one row to another row. And if your copies are at the row granularity, this is great. So that's the idea, basically. And 2 consecutive activates, negligible hardware cost. This is part of the idea because this is within a subarray, how you do it. Now, it's quite interesting because we said negligible hardware cost. Later work, building on our experimental DRAM testing infrastructure showed that you could actually do this in real DRAM chips by violating the timing parameters. This was actually quite clever, I think. What they did was, today DRAM chips are supposed to have an activate to activate latency, and you have to obey that. But if you bring that latency down and down and down such that 2 activates are close to each other, you need to do it carefully, of course, you need to find a good sweet spot. It will essentially imitate what we're proposing, 2 consecutive activates. And you could actually do this reliably in most existing DRAM chips, according to their results, which we replicated recently in our infrastructure also, which I'm going to talk about. So that's the idea. That's the compute DRAM paper that was published in Micro 2019. Our paper was published in Micro 2013. So 6 years later, somebody figured out how to do this in off-the-shelf DRAM just by just changing the memory control. So this idea is not just like circuit level theory, it's real. Even though the DRAM chip is not specified or designed to do this. So that's, I think, important because that's quite powerful because that shows that nobody designed the DRAM chip to do this, but you can do this operation, data copy operation, by treating it in a different way, meaning violating the timing parameters. So I think that's actually quite promising for analog operations as well, as we will also discuss. Okay, I'm not going to discuss how to do this between banks because a DRAM chip clearly is not just one subarray. You have many, many subarrays and many, many banks. Well, fewer banks, but still more than one. You can do the copy between banks also. You can copy data from one bank to another bank because all of the circuitry actually exists. It's all about orchestration. I like using that term. Orchestrating that existing circuitry such that one bank is put into read mode, another bank is put into write mode, essentially, because all of that circuitry already exists. And there, the granularity can be even 1 byte based. You can copy 1 byte from one bank to another bank. Between subarrays, it's a bit tougher because there's no direct connectivity between different subarrays in a single bank. But we actually have solutions to that also that I'm not going to talk about today. So if you start imagining what you can do in a DRAM chip to reduce data movement overheads so that you can do the data movement within the DRAM chip as much as possible, as efficiently as possible, you can optimize the design of the DRAM chip as well for that purpose. And I think you gain a lot of benefits. Okay, so part of the benefits that we showed in this original paper is this. Within a subarray, you get more than 10x performance improvement on a copy operation, latency improvement, and more than 70x DRAM energy, memory energy improvement. And this reflects itself in the application level also, depending on how much copy and initialization your application does. I use initialization and copy together because initialization is really a special case of copyright. When you initialize a row, for example, you're copying a value to that row. And that value is not coming from anywhere in memory, but you just produce that value somehow, right? Okay, so more on this in this paper. And as I said, more recently, inspired from this compute DRAM work, we have essentially tried to replicate this compute DRAM paper's results, and we were able to do that. And we released this open source framework where you can essentially do these end-to-end studies where run an application and observe the benefits of row clone on that application. And in this paper, we describe what we found. And people can use it if they're interested. This is a real picture of the system. We call it processing in memory enabled DIM, but it's enabled by, in this particular case, by just changing the timing parameters in the memory controller. And then we have a software stack on top of this, where the application can do, for example, a row clone copy. And then all of that gets called on the FPGA, and the FPGA can actually do this FPGA-based memory controller can do the copy for the system in the memory so that that copy happens only inside the DRAM chip. So that's the idea. And if people are interested in using this, it's all online, open source. We're happy to help, basically. Yes, please.
Like quite simple things. Basically, add another command to your DRAM that says row clone this to this, add it to your memory subsystem, and everything gets faster. Is there an easy explanation for that? Or?
I think there are multiple easy explanations for that, probably. I don't know if there's one easy explanation. So, okay, I think this is the mindset that I'm going to talk about later on. It's, and particularly in the memory industry, the mindset is business as usual. Basically, business as usual is great. Let's push business as usual more. That's the mindset, basically. And there are reasons for it, certainly. Yeah, I mean, I agree with you. Everything you said makes perfect sense to me. The reason is that business as usual. Why? So what goes into that business as usual? Cost, partially, of adding another command, for example. And that's, usually, if you want to add another command to the standard DRAM interface, you have to go through a body called JEDEC. That's the standards. I cannot call it a corporation, but standards body, let's say. Body is the right word, I think. That consists of many, many companies. I mean, you can be a part of JEDEC also and be a force for good over there, but good luck. Basically, there are a lot of manufacturers over there, also vendors, also like high-level consumers, etc. And it's a huge political mess where people need to agree on that command being incorporated. At that point, it becomes completely political. And it's not just about how much gain we're going to have. It's about how much benefit each person is going to have and how much are we going to lose, right? What do you mean? Or to hurt the other one, exactly, yeah. So, okay, Matthias knows this is what I'm talking about. So, or to hurt someone else, basically. So it becomes a huge political mess. And this is, I think, like when I talk about what's limiting innovation in the world or in memory today, is this is one of the high things, basically. This, the fact that you cannot make easy changes to this interface without going through this body makes it very hard. So let me give you an example. DDR4, DDR5. It took about 9 years, I think, to go from DDR4 to DDR5. And the differences, you look at DDR4 and DDR5, not that much. I don't see that many new commands. RFM is being one of them. I mean, in the grand scheme of things, not that much, basically. Maybe you can correct me on that 9 years, people, but I think it's about 9 years. Yeah, it's correct. Okay. Yeah. So that's an example. Does that answer your question?
Yeah, it makes sense. It's a sad thing, but
it's a very, very sad thing. Yes, yes. So I think what we have been doing in the global scale is we've carved ourselves a bureaucracy that is really hurting us in the entire system level. And we've been basically punishing ourselves in that bureaucracy. Even though a lot of people technically know what's good and what should be done, they cannot do it. Even though they want to do it, they cannot do it. That's very sad. So something needs to break, basically. I think that, I'm not going to call it a revolution needs to happen, but people need to get out of this mindset, basically. Yes, maybe there's another, yeah. Yeah. No, we also have, but I'm going to briefly mention a random number generator inside the DRAM, purely in DRAM. We have the row clone feature, at least in the publicly available framework, we have the row clone feature and DRange, which I'm going to briefly talk about. You can generate random numbers inside DRAM. And this can also supply to the application that's running. So you call the rand function and you get the random number, except the random number happens to be generated inside the DRAM by violating timing parameters. It's a true random number generator. Yeah, you can think of it that way. I'll mention it when we get to it, yes. But we also have a non-public version that can do what I'm going to describe next, which is bitwise operations. It's much less reliable than existing DRAM chips, but we can potentially share it, yes. I need to discuss with my students. Yeah, potentially we can share it. Very happy to encourage more work in this direction. Yeah. I think part of the mindset change may happen with this sort of prototypes, for example, right? People keep using it and yeah. Yeah.
But the problem is that they say, yeah, we will not build one chip for automotive, but one DRAM chip that goes to the smartphone, that goes to the servers for the MacBooks or whatever. So the business model is probably that, but even more than the standardization, kind of us make your progress.
Yeah, exactly. I mean, yeah, absolutely. I was going to talk about the business model as part of the other mindset issues. Yes, I agree with that. People have some sort of business model they also cannot get out of, basically. Yeah. And there are good reasons for it also, right? Because there's testing costs. Any additional feature you add to the memory chip requires some sort of testing, clearly, to make it work. And that testing cost in a relatively low margin business like DRAM, which has happened to become that way, it adds more cost. Then the question becomes, who's going to bear that cost, right? Are people going to pay more for it? And DRAM manufacturers usually are not great at, let's say, predicting who's going to pay for it. So they're usually very conservative, saying that by default, nobody's going to pay for it. And that's why that's the self-fulfilling prophecy that DRAM doesn't improve, because people think nobody's going to pay for it and they don't improve, add new features. That's why the business as usual continues, basically.
You see the RowHammer, for example, you could solve RowHammer easily by changing the array design back to one transistor memory.
Yeah, that may be very difficult. Yeah. Yeah, exactly. You lose density. Yeah, that's hard. Yeah.
But then the point is, are they ready to give up half the density? Because it's defined by cost per bit, and then for them, what is more important is yield.
Yeah, yeah.
They have proven that yield, which they don't want to disturb. This is the thing.
Yeah. Okay, I mean, we can have more. This goes more into the DRAM reliability, RowHammer deep dive, let's say. That if people are interested, we can go into it, but maybe we'll be up here until the morning if we do that. Which is also fascinating, clearly. Yeah, we can discuss it, I think, offline. This is certainly unfortunate, but I think people are hopefully realizing more and more. Let's see. It's not fast enough for certainly people like us, maybe, but people are realizing more and more. People are, for example, putting RowHammer solutions. However, let's say on non-robust they may be today, they're at least trying. Okay, so there's a lot more to talk about actually rowclone and improvements on rowclone, let's say, to improve data movement. I think I don't have time, but you can certainly ask me or look at the papers, etc. I don't have a list of the papers here, but this lecture contains the list of papers. For example, we have work on connecting the subarrays together. I think this is an interesting idea also. If you can connect the subarrays together, you can actually achieve a lot of benefits, including moving data fast between the subarrays, including faster pre-charging, lower latency, for example, and also faster, better caching potentially inside DRAM. We've demonstrated that with a paper called Low-Cost Interlinked Subarrays, LISA, in HPCA 2016, that improves on the connectivity in DRAM. So if you add more connectivity to DRAM, you actually get more benefits in terms of data movement as well as other things. Okay, but the mindset is, I think, kind of similar. Again, you're using memory as an accelerator, in this particular case, accelerating data movement and initialization operations. And you can say that I'm cheating. Yes, I'm cheating because these are not computation, right? So let's take a look at computation then. And again, I'm using the perspective of DRAM again. Can we do computation in DRAM using DRAM without adding logic? We may add a little bit supporting structures, as we will discuss in one particular case. Well, in both cases, actually. So basically, the good news is we can support simple operations like in DRAM and or not majority function bitwise operations at low cost using analog computation capability of DRAM. And the basic idea is to activate multiple rows concurrently. And this happens to perform computation based on circuit level principles. And performance and energy improvements are actually quite significant. And this is introduced in this paper. There's an older archive version that's called BuddyRAM, because this was rejected multiple times also. Okay, so before I go into the idea over here, I think I should mention that I'm not going to talk about the emerging memory technologies in this tutorial. I think they're fascinating also, and they're important to examine because they also enable more opportunities and different opportunities. It was shown that the ideas that I'm going to describe are applicable to emerging non-volatile memory technologies, but they can do more. Because fundamentally, whenever you do a read in a non-volatile memory technology, it's not destructive. So you can move the data less compared to DRAM, even less. That's one aspect of it. The other aspect of it is that a lot of these technologies have some sort of 3D array, crossbar array structure. And people have shown that you can do matrix vector multiplication in this crossbar array by exploiting Kirchhoff's laws, essentially. which is analog computation essentially, right? So there's a lot of literature on that topic and experimental chips that are built, and they're all actually quite interesting. There should be more work in that area that I'm not going to talk about. I'm going to talk about DRAM, which exists, right? I mean, the other technologies exist, but they're not mature enough yet, perhaps with the exception of Intel's 3D X-Point, which is already in the market. Okay, so let's take a look at DRAM. So if you want to imagine that you have 3 bits over here. These 3 bits, three capacitors belong to 3 word lines. And imagine that each word line, each row has 8 kilobytes of these bits, let's say. So what I'm going to describe, you can do on 8 kilobytes concurrently at the same time. And of course, this is one subarray. If you enable all of the subarrays to be able to concurrently do this, then you can potentially do this on 8 million bytes, let's say. So it could be actually, you could do all of what I'm going to describe on all of the, well, all is probably too strong, but many of the DRAM cells in memory. Of course, you need to provision the power, provision the cooling, and provision the reliability for that purpose. But let's take a look at 3 bits. If you concurrently activate the 3 rows that these 3 cells belong to, in an ideal circuit, what the result you get at the sense amplifier is a majority function, bitwise majority function. Basically, what happens is you connect these 3 cells. If 2 of these cells are charged, you get the charge state at the end. If 2 of these cells are discharged, you get the discharge state at the end, because the charge levels dominate, or the lack of charge dominates, right? Because a DRAM works essentially by charge sharing, and the perturbation that happens based on the charge level in the capacitors when it shares charge with the bit line. So if 2 capacitors are charged and they share their charge with the bit line, they dominate the non-charged capacitor. As a result, the function that you get, the result that you get is the charge state at the end, and vice versa for the discharge state. So basically you have a bitwise majority function, right? Which is really nice. Now you can start thinking of, oh, can I implement my algorithm as a function of bitwise majority functions that's inside the DRAM chip? But you can do, I mean, with simple Boolean manipulation, you can set C to 1 and you get the OR of A and B, and C to 0 and you get the AND of A and B. So that's good. Now you can do OR and majority. The question is, how do you do NOT? Well, you don't have to do NOT because the complement, whenever you read a row, you basically sense the value on this side of the sense amplifier, and the other side of the sense amplifier has the complement. Now, by doing some, let's say, intrusive modifications to the subarray, you can feed that value back into the subarray. That's the idea that we propose over here. If you can do that, now you have the majority function and NOT, which is functionally complete, or AND and NOT, which is functionally complete, or AND or and NOT, which is functionally complete. Yeah, go ahead. Oh, okay. Yeah, that's a good question. It's not a nasty question because that's something that needs to be solved for this to work. So after you do this, as I said over here, as I showed over here, which I didn't go through the animation, all of the cells become charged, which is the majority function value, right? A result of the majority function value. So we don't propose, basically you lose the ABC values that you originally had. So what we propose in this work is to have a special part of the DRAM subarray such that it's dedicated to doing these operations. Everywhere else in the DRAM subarray, you need to move the data from there to the special part of the DRAM subarray using row clone, essentially. That's the idea. Yeah, of course, this modifies the subarray, but it has other benefits, not just recovering the charges, but now you're actually limiting the possibility of operations to only that portion. So you don't need to have 3 address decoders, which is a huge cost. Yeah, that answers your question, hopefully. Okay. Of course, yeah, so basically it's a bit intrusive, as you can see, right? It's not, it gets out of this mindset of, oh, I cannot modify the subarray, which is the mindset of the manufacturers. But maybe we should really be rethinking the subarray also going into the future, right? If memory is so important. If memory is not important, yeah, we should do business as usual. Okay, yes. Mm. Yeah, potentially. I mean, certainly, yes. I think that I'm not suggesting that the knot is easy to feed back in. You could potentially feed it into the other subarray. That's a potential possibility to think about. And then use the Lisa substrate that I briefly mentioned. So I think there are other potential solutions to this issue. Yeah, that's a possibility, but that also has issues, right? Yeah. Mm-hmm. Exactly, yes. Yeah, certainly. I think there's certainly benefit of looking at adding more logic to the sense amplifier region, which I did not talk about, but yes, it does go into the other class. From a purist perspective, now it's not processing using memory anymore. You're modifying something. I mean, you're not modifying something. You're adding logic to do computation basically over there. But yes, I agree. I think that all of that needs to be explored. What we proposed, like initially in 2015-ish, is not, in my opinion, the best design that can ever be, right? Yeah. Yeah, but not. I think you need to have a knot also. You cannot do much. You cannot be functionally complete without a knot. Oh, okay, yeah, you have multiple. Okay, sure. But multiplexer can implement a knot, right? That's why. Yeah. But yeah, exactly. So okay, so that's the idea over here. And I should say that the compute DRAM work also showed that for a very limited set of DRAM chips, this majority function is possible without changing the DRAM chip. This is off-the-shelf DRAM chips, and by again reducing the timing parameters between activate, precharge, and another activate, such that you kind of mimic this triple row activation that we discussed. This is, of course, row clone works on most DRAM chips, let's say, where you can actually modify the timing parameters or reduce the activate to activate latencies. But this one doesn't work in a majority of DRAM chips because getting this triple row activation to happen is not easy. It's very circuit specific, let's say, because the DRAM chip is not designed for triple row activation. But I think I still find it amazing that it still happens in some DRAM chips, even though the DRAM chip was not designed for that purpose. Yeah. This is the compute DRAM paper that I mentioned. Yes. Yeah, that's the compute DRAM paper. Yeah, that's what I mentioned basically. It doesn't work on many DRAM chips because it's not an easy thing to get it to work just by modifying the timing parameters. You'll need to have a triple row activation function. Okay, so what is the benefit? Now that's the question. I think you can actually implement anything on top of this, in my opinion, and we're going to talk about some work that tries to further this. You just need to rethink your algorithm such that it maps to the substrate, because fundamentally the substrate is a functionally complete tract. You just need to think differently. But there's some workload that people have already been thinking a lot in terms of bulk bitwise operations, and those are great fits for this sort of substrate to begin with. For example, databases use bitmap indices a lot. Bitweaving database was specifically developed for bulk bitwise, maximizing bulk bitwise operations so that you can do these database operations on GPUs, for example. Microsoft is a web search engine that operates on similar principles to those databases. And there are a bunch of other types of workloads that do a lot of bitwise operations, set operations, for example. And more recently, we showed that we actually developed an ISA called SISA, set ISA, which supports set operations. And we showed that a lot of graph pattern mining algorithms can be executed very efficiently using an ambit-like substrate because a lot of the graph algorithms are translated into these bulk bitwise set operations, which is fascinating, I think. This was published in Micro 2021. I had this in one of the earlier works. So that's an example of complete algorithm, including ISA rethinking, so that you take advantage of some bit level parallelism in your graph pattern mining and exploit it using processing using memory. Okay, so I'll just give you one example over here, which is from the bit weaving database that I mentioned over here, which was published in 2013, as you can see. And if you do the hard task of mapping this database queries onto an Mbit-like substrate, you get significant performance improvement. And this is all in simulation, clearly, but you get large performance improvements or end-to-end performance improvements on latencies of different queries. Okay, we still have time, right? Okay. How long do we go until? Okay, 1820. Yeah. Okay, we have time, I think. Let me get some more water, giving the opportunity for people to ask questions. Yeah, so there are a lot of other issues over here. I should mention a couple of them. That was our original paper. I should put the archive version over there also, because it's very similar to the original paper, except it got rejected 4 times while remaining very similar. Of course, some things, writing, evaluation improved, but yeah. Like if I had more time, I would share some of those reviews, but let's not go into that right now. I share that with my students in graduate class, and they get relieved because they receive similarly, let's say, unreasonable reviews, let's say. That's good. I think it's good practice to share it. Okay, so I'm mentioning this paper because here we also look at some future work. So one of the issues I think with this IEDM execution engines is really error correction codes. And I think this is an issue that people should be thinking and working on more. Because whenever you do row clone, for example, or block bitwise Mbit-like operations, triple row activation, how do you correct the errors, right? If errors come about, you're doing nothing basically to correct the errors. And the question is, how do you correct the errors? Today's DRAM chips incorporate IEDM ECC, error correcting codes. So there's some error correction, but can you actually do that for these operations? It remains to be seen. And there's relatively little work in that area also. Okay, there are a bunch of other issues that we talk about in this paper that I'm not going to discuss right now. But okay, then a few years later, well, we asked the question, can we actually generalize this? Can we make it easier to add any kind of arbitrary operation? And can we take a more system level perspective and make this Mbit work in a much better way? And that's the idea of SimDRAM, I will briefly describe. And this is essentially a framework that enables a user programmer to define any kind of operation, and that enables the implementation of that operation using Mbit operations. So user provides a desired operation. It could be a convolution, for example, using and or not logic. Hopefully this is simple for people to think about. It could be, I don't know, matrix multiplication. It could be something. It could be any granularity, actually. It doesn't matter. It could be something that we don't already implement. It could even be XOR, right? XOR can be defined based on and or not. And the first step of this framework is to generate majority not logic using a majority murder graph. This actually, we borrow a lot from the design automation community to do this conversion and optimization of that majority inverter graph. And the second step is based on that majority not logic, we generate a sequence of DRAM commands to implement that function. And we use majority or not because people have actually done a lot of work in the CAD community to optimize that majority and not. There's a lot of work actually from Nani de Michele's group in EPFL. We borrow a lot of their work in infrastructure. That's why we do the majority not optimization. And then you translate the majority not optimization to generate a sequence of DRAM commands to implement that optimization. There's something that you need to do to take into account the constraints of the DRAM device, like this part of the array where you can do the operations, because it's not infinite clearly. So there's some allocation and management that you need to do. It's not easy to generate it basically, but once you generate it, this forms your microprogram essentially. This is the microprogram that sits in the memory controller that implements your new instruction. Instruction can be defined, user defined, as you can see. We call it bulk bitwise operation new. And for each bulk bitwise operation that user defines, you have a microprogram associated with it and this sits in the memory controller, it gets brought into the memory controller. And when the user actually executes a program that calls one of these instructions, that instruction gets offloaded to the memory controller, which fetches the microprogram and executes that microprogram. That's the idea. So this way you can implement any operation actually, as long as you're able to specify it using this and or not logic or majority not logic to begin with. Okay, I think I've explained all of the steps. And the paper also handles a lot of other issues that you need to deal with. Because this is block bitwise computation, you're doing bit serial computation. And the format of the data that you have in your caches is not really bit serial. So you need to have some transposition that you need to do when you actually copy data from into your caches and out of your caches. So there are a lot of other issues that you need to deal with, and this framework handles them. Yes, please.
So question, I understand this way you're avoiding the caches, but isn't that again moving the processor closer to the memory if you're offloading the logic to the memory controller, which in this case acts as the CPU?
So yes, I think this is, I think if I understand your question correctly, this is a processing near memory approach. Yes, but it's taking advantage of processing using memory. So I would say this is a kind of a hybrid approach. You have the controller, this control unit that is taking advantage of processing using memory operations to execute your whatever function you offload.
Okay, maybe I missed that part. So which part on the image is actually doing computation in memory?
So these activate pre-charge operations. Okay, maybe I should have explained this. Some of these are triple row activation and row clone operations. Does that make sense? Because you have the majority and not, and some row clone operations to copy the data. You translate them into DRAM commands that do triple row activation, which is not shown nicely here, but the paper explains what this terminology. This terminology actually was borrowed from the earlier papers that I kind of hid from you. Okay, so all of these are basically row clone and ambit operations that are done on the DRAM chip. Yes.
If you think again about implementing this in the chip, you certainly need to do some changes to the chip, at least implement a command for row clone, and maybe for the triple application.
Yeah.
So you need to change the chips anyway. Would it be easier than to just include like AND and OR gate into the SEM amplifier? I don't know how complex these are, but I would expect them not to grow too much if you just include one or two logic gates, and you need to change the chips anyway. So I'm not too convinced why this majority in the analog circuitry thing really helps you.
So that's a good question, basically. That goes now into the cost of including more gates, right? You need to include, let's say, like, what do you include? Do you include AND or not? All of them? Yeah. Well, for completeness, you just need AND or not, right? or yeah, one of the two, basically. Yeah, exactly. So I think that becomes interesting. I think there are good arguments maybe to do so, but also there are good arguments maybe not to do so. So I think that requires some more analysis for sure. But this is something we show that you can do. Certainly you can do the additional logic, but this is, I think, fascinating because you're taking advantage of the existing technology. Yeah. 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 Yeah, I think it's good to think about this. Yes, I think it's important to think about it actually, like what is a better way of doing it? Yeah, I have my opinions, but maybe we can discuss it later. Yeah. Okay. Okay, so let's move on. So if you actually do this, in the paper evaluates a lot, there's a lot of interesting evaluation in the paper. Just one example evaluation is we look at 16 different complex DRAM operations and 7 real world applications. And we basically see even more performance improvements than we have shown with Ambit because we're kind of optimizing the system right now, right? And you can see that, yeah, the throughput and energy efficiency improvements are high and the performance over at CPU and GPU are quite high as well. You can read the paper for more detail. But I think this sort of framework is going to be important for developing like real systems that can benefit from processing using memory. Also processing near memory. This is, in this example, this is a framework for processing using memory clearly that takes advantage of a controller near memory. But I think processing near memory also requires this sort of framework going into the future, like as to what to offload, for example, what kind of function can be implemented down there. Okay, so I will briefly mention what we have discussed earlier, but you can do more in DRAM. And I think it's good to understand what we can do in DRAM, looking at the technology with a mindset that, oh, this can also do some computation inherently. What else can we do? So we've shown that you could actually create physical unclonable functions in DRAM. This is because of the latency reliability trade-off. As you reduce the latency of a DRAM cell, at some point, the cell fails, basically fails operating. And this failure pattern is specific to the device, meaning that it becomes a signature of the device. And you can identify different devices based on this. Essentially, this is a physical unclonable function. So that's one way of doing it. And this clearly enables security applications. Similarly, we've shown that you can actually generate true random numbers in DRAM. Yes. Yes.
Why use the DRAM protocol?
I like that answer. Why not? Why do you use anything else for Prof? So I think the space of challenge response pair is much smaller in SRAM, whereas in DRAM you have a huge space, right? In Flash you have even huger space, of course. Yeah, sure. Mm-hmm. Yeah, sure. But now you answered the question yourself. Thank you. Yes, there's another thing. Oh, you're going to answer. Okay, good. So I like the why not answer because. So I think in my experience, it's good to uncover these things because people will find applications for it. And even if people don't find applications, maybe they'll get inspired to do things differently in some way. So that's another way of answering it, in my opinion. Okay, so the other, I mean, similar to PUFs, exploiting a very similar trade-off, latency reliability trade-off, you can generate random numbers, and these are true random numbers to our knowledge. And the idea is you reduce the latency of a DRAM cell. Some cells fail randomly. Sometimes they fail, sometimes they don't fail. And this is about 50% probability. If you can identify those cells, profile them, they become nice random number generators, true random number generators. And according to what we know about DRAM and what you can understand, these are true random number generators because they're based on the stochastic noise that you have in the bit line and the sense amplifier. So it's interesting, I think. Yeah. So there's prior work that proposed it and we compared to it. Mm-hmm. So, okay. So there are two issues here, two questions. One is this truly random? You need to recover some of those noise. I think a lot of true random number generations actually require some sort of post-processing still to get rid of those things. And once you get rid of those things, actually you get what you get is truly random. The other question is, refresh, retention errors are a bit different. We actually, there's a lot of work that did this using retention errors. And yes, if you, so there are two issues. One is you need to select the cells very carefully and also do some post-processing. In either of these, if you fail, yes, you may not get a truly random number. In the issue of refresh, retention errors, retention errors, if you do both of them, again, retention errors lead to a true random number generator, but they're too slow, basically, to induce. Latency is here, you reduce the latency, meaning you're reducing the latency of random number generator. But for retention errors, for example, you need to wait for 40 seconds or 40 hours sometimes to get an error, basically. And that's not a great true, it is a true random number generator, but not a great one, as you can see, right? So the bandwidth and the latency is not very high. We compared to it actually with real experiments in this particular paper. That's a good question. Okay, so this is actually interesting, but there is more you can do. This is a more recent work that was 2 years after this. where we showed that another primitive can lead to true random numbers in real DRAM chips. And this is the idea of 4-row activation, which is also quite interesting. So you activate 4 rows at the same time. Clearly, you cannot get a majority function over here in the perfect circuitry. But what the result you get is a random number in not all of the cells, but you need to, again, carefully select some of these cells. And with real chips, we showed that you get a much better random number generator compared to this earlier random number generator that we developed. So I think this is also fascinating. Really, if you have a processing in memory substrate, if you offload security critical applications, you may actually need both puffs and random numbers over there. And yes. Yeah. So proof in terms of, so maybe I should be more specific. In terms of throughput, this was much better because it could induce a lot more randomness in many more cells. Yeah, that's the reason. Yeah, that's a good question. In terms of latency, I think this was a bit slower actually. Yeah. But in terms of randomness, it's a bit hard to compare which one's better. Yes, I'm not suggesting it's a better in terms of, let's say, true randomness. I don't know how to compare that. There's some theory folks that have some. Yeah, certainly. But those tests really, so yeah, they're fine tests. And like NIST tests, for example, National Institute of Standards test, they're fine, but they're not, they basically tell you a threshold. And if you are over that threshold, okay, you pass the test. But you cannot, yeah, exactly. You cannot compare, I think, based on the values that you get, which one's the better one. You can do entropy. And we did entropy. And entropy here is a bit higher. But again, it may depend on the chips that you test also, right? That's, yeah. Yeah. Yeah, I think the theory of random number generation folks are quite fascinated by how to do this. And I don't know if they have a way, at least a practical way of doing it. Okay. And this is a more recent work. Again, we need to look at this end-to-end also. PyDRAM work does on end-to-end also, but there are some other issues PyDRAM doesn't solve. There are like actually more issues that you need to solve to integrate this into a real system, and we solve some of those issues over here. So maybe there's some other better true random number generators out there. Who knows? Okay, let me talk about adoption challenges. We've kind of been talking about them, but I think this is really a key issue. How do we enable the adoption of this? We've talked about different ideas, how to enable adoption of them. I think processing in memory in particular is something that's finally picking up, right? 2019, UpMem produced the first commercially available chip. Now people are proposing, like people like Samsung, Hynix, Alibaba, they're building their own prototypes, maybe using them in real systems. We don't know fully, on some of the closed ones at least. So it's good, but maybe we need to do a lot more to enable adoption. Like whenever you design hardware, it's really important to get it adopted, right? I think my favorite example over here is, do people here know about Arvind at MIT? Probably. The older folks do, of course. So you don't need to raise your hands. So Arvind, when I was a graduate, that stuck with me a lot is, he said, we did all of this data flow work. It was great. There was a lot of beautiful hardware building. And he said, but the most important mistake we made was not deal with the software, basically. Meaning that's the adoption. That's what really enables the adoption. Now, clear data flow had a lot of successes, especially more recently, right, with FPGAs, etc. But maybe he was envisioning perhaps a future where he worked on the software and enabled it right away. Who knows? And I think similar issues exist with any hardware. And this is, again, hardware. And I think in adoption, hardware is not the hard thing. Hardware companies may think it's the hard thing, but it's really the higher levels of the stack, right? And these, I think, are a list of issues, potential barriers to adoption. What applications and software, how do they use it? How do people use it easily? What kind of system and security support is provided for it so that it integrates well with the system? Like people are used to coherence, certain synchronization methods, virtual memory, some expectations on isolation, different communication interfaces. How do you make it work, at least efficiently with these? How do you build runtime and compilation systems that, again, enable the use of this nicely? Data mapping, for example. If people don't want to do their own data mapping, how do you do your data mapping for processing in memory? And how do you enable people to actually assess the benefits and feasibility of this infrastructures, basically? So I think there's a whole list of issues which are all broad research directions and questions, in my opinion. Maybe more than anything else, we should really change the mindset, right? I think that's why my focus is on mindset. If you change the mindset, and if you say, okay, I'm going to do it, maybe you can solve a lot of those issues, right? But if your mindset is, for example, oh, this requires changes to data mapping. Yes, it does require changes to data mapping, and you should rethink your data mapping to make it work, right? And maybe you should rethink how to do the data mapping transparently to the programmer so that this works. Yeah. Okay, so I think that's really what I mean by we need to revisit the entire stack in the end, but maybe step by step we can get there slowly. So that's why I think we and other people have been looking at accelerating applications, right? Why do the application level studies? Is it boring? Does it provide novel insights? You can always ask these questions. I think the key is basically it shows that there are many applications that can benefit and there are ways of taking advantage of it. So I'm not going to bore you with all these application level studies, some of which we covered already. How do you keep it simple? I think is important. Like SimDRAM framework tried to do that. SimDRAM is an example of PIM-enabled instructions, actually, even though we did not discuss PIM-enabled instructions. So this is a way of enabling you just add another instruction that can potentially be executed on the memory side. That's the idea. And there are other issues. You can decide whether or not to execute on the memory side, of course. How do you maintain coherence? Now we're getting into more thorny issues, let's say. You have some data in caches, some data in the processor. How do you do the coherence? Some data in the memory, some data in caches, and you're operating on the memory side. How do you keep things coherent? And this is important, clearly. This is an issue that we have worked on. There needs to be more solutions to it because traditional coherence mechanisms actually don't work well. Ideal benefits are actually quite high. This picture doesn't do justice to it because this is with smaller data sets. But basically, if you use traditional coherence mechanisms, you don't get the benefits of processing in memory. Your performance is very similar to existing systems on these tough applications, let's say. But if you actually have a better coherence mechanism, you get much higher performance improvements. Okay, so coherence is interesting, and we have some papers on it. I haven't seen a lot of work in this direction, actually. I think there should be more work in this direction. An even more thorny issue that opens up, well, I should talk about synchronization. I think synchronization is also important, and we have some recent work on that topic also, which can be solved with additional logic. But I think perhaps the most thorny issue is virtual memory. I think this is perhaps the most thorny issue we have in our systems today, independently of processing in memory, frankly. We have this virtual memory subsystem that was developed since 1960s, in the 1960s, actually late 1950s, and we're still stuck with it. We've been doing incremental improvements on it, and it's not working very well, in my opinion. So we have 5 levels of caching. I can show you 3 or 4 levels of caching on the virtual memory subsystem also. So now, are we doing the right thing with virtual memory? It becomes a question also. I should have done that. I showed this picture to my first-year students in bachelor's class at the end. So we have data. We have many, many layers of caching for data. And then we have metadata to locate the data, which is the virtual memory subsystem, and protect the data also. We kind of assign multiple things to the virtual memory subsystem. And that requires many levels of caching also. And not just only caching, some accelerators like page walkers, TLB mishandlers, etc. So there's huge real estate that's devoted to it. Yet many applications don't want it or don't care, right? Because some applications have huge amounts of memory allocated, and maybe you don't need a tough page level, 4 kilobyte level virtual memory system. Okay, that's my pitch for virtual memory, rethinking the virtual memory, I think. I think that's a huge mess, independently of the existence of processing in memory. But processing in memory, of course, complicates it a little bit. If you have translation, virtual memory translation that is needed by if your granularity of offloading is large, this becomes even potentially larger. So we really need to rethink how we deal with virtual memory for processing in memory. But I think my general point is we really need to rethink how we're dealing with virtual memory today. It's not scaling very well. Okay, we have some papers on that topic that I'm happy to discuss. It's not on these slides over here. Okay, any questions?
They do actually.
Okay, sure.
I mean, this is an interesting point, Onur, about what you brought up. But you're saying it doesn't scale well because you know all the stuff that we need to keep in order to track all this stuff is growing.
Yeah, growing.
But then our memory is growing.
Yeah.
So is the ratio growing?
So that's a good question. I think our memories are growing so much that a lot of the programs today are actually quite resident in the physical memory. So maybe we don't really need the virtual memory.
So that's one.
Yeah, that's one possible. Yeah.
If we don't need that, then we don't use it. But you don't actually make the case. Let's throw it away. You said let's reevaluate.
Exactly.
Which means, well, we need that, but we need something in between.
Maybe we need. Yeah, that's a good question. Basically, I don't want to specify any solution, but we need to rethink it so that we get the benefits it provides. Right, because there's certainly some benefits we want, like relocatability of code, isolation between processes, etc. But maybe we don't want this small granularity pages. Maybe we need a different way of thinking. Yeah, maybe there's something in between. I don't know. I'm not suggesting there should be some specific solution. Like we have our solution, but we can talk about it separately. And I think it also needs work too, because, yeah. So a lot of the literature in virtual memory, unfortunately, is how do we do incremental improvements into virtual memory? And yes, you can do that. It's like making incremental improvements to caching, right? But can we do it in a completely different way? Becomes a good question, I think.
This last point you raised has been the curse of the computer architecture community for the last 50 years. And I mean, they seem to be in a groove over there of this incremental improvement. So you come and you say, well, let's change everything. But obviously, these people who believe in that particular way.
Sure, yeah.
So how do you make sure that you make inroads?
Yeah, I think virtual memory, it needs to start, and it's starting. There's more work in this area. But I think the example is processing in memory, for example. There's some inroads. People are moving in that direction right now, right? Yeah, I don't know. I don't have a perfect answer to this. I think people are more open to, let's say, newer ideas in the architecture community also today.
In some sense, the computer architecture community seems to be, getting towards a local groove, local optimization groove.
Yeah, sometimes it happens, yeah.
And in some sense, you're questioning that local optimization.
Yeah, I like that.
Are you hopeful?
I'm hopeful, yeah, I'm hopeful. I mean, with virtual memory, it's a bit tougher, right? Because, it has not been looked at, let's say, fundamentally for so long. That's the sad part. Processing in memory, at least, people have proposed different ways of doing it, never succeeded. Today, hopefully, we're going to succeed. But virtual memory, I think I'm hopeful, but we'll see, right? No guarantees. Yes. Yeah.
For example, process separation. But if you look a little bit further into the future, I think that in the future we will have non-volatile memory, right? Start to just fix your PCM and so on. We have endless memory, right? And that could be really a good reason to rethink the virtual memory. But still the other branches that we have.
Yeah, so I mean, I agree fundamentally with what you say. I'm not going to claim that in the future we'll have only non-volatile memories, but that's the argument. That's the argument we make in the paper. We'll have heterogeneous memories. Some of them DRAM, PCM, whatever. Flash also will be part of that memory system potentially. So we need to rethink it. So virtual memory actually doesn't do very well with heterogeneous systems. We showed a lot of data in the paper. This was in ISCA 2020. We called the virtual block interface. So that's one reason. I agree with you. That's one reason why we should rethink also. Virtualization is another reason, right? On top of virtual memory, you have another level of virtualization, which exacerbates everything that you do. And that actually doesn't do very well. If you rethink how you design the translation, you can actually do much better, basically. Okay. Okay. Yes, please.
One of the problems in the cache is complex pattern for accessing. Can help this problem or not?
So when you say complex pattern for accessing, what does that mean? It's like random accesses, or?
No, for example, when you have a complex cache, it's not for topology. For example,
yeah, yeah. Sure.
When you change the matrix as a response matrix or something like this, you make the pattern complex.
Yeah, certainly. I think you need to solve those issues in the memory side also, yes. So in some of the processing near memory approaches, you can still have caches that benefit from it.
I know, but some of the operations within the memory.
Yeah.
I'm saying that this helps this problem.
Oh, okay. Does this help that problem? I guess depends on how you lay out your data. I think depending on your data layout, it may help or it may hurt. But I think fundamentally, if you change your access patterns, you need to relay out your data to get the best performance out of your cache structure or memory structure. And if you have so people actually have proposed near memory logic to do this transposition of data. So processing near memory certainly helps with the transposition of data so that you can get the best access pattern in memory or inside the caches also. Yeah.
No, I think so, for example, most of the time we need to take off to the cache to compute some internet stuff. Just an example. Can help this case or not? For example, some of the
Yeah, certainly. I mean, if your intermediate results stay in processing in memory, in a lot of these applications, that's what we see. You don't need to bring the intermediate results to anywhere. Yeah. Okay, sure. Okay. So let's talk about processing in memory in the real world a little bit, go into a little bit more detail. So if I was giving this in 2019, you would see none of these chips at the bottom, basically, as you can see. None of it that's labeled after 2019. You just see the top. So this is a good time, basically. And this is UpMem. Let me give you some examples of this. This company in France, which we're working with actually, has produced these DIMMs and DRAM chips actually. Each DRAM chip has a processor in it. They call the DPU, DRAM processing unit. And this DRAM processor unit is next to a bank, essentially. And these are real chips that we have experimented with, and we have written papers about it. This is one video. So you can see the processor. This is processing near memory approach. This is a 64 megabyte DRAM bank. And you can see that this is a processor, very similar to existing processors. It's an in-order, multi-threaded pipeline. It has a cache instruction memory. I should call scratch pads. Basically, these are scratch pads that you use for instructions and data, essentially. So it looks very similar to what we do today, except the processors are distributed across all of the banks. Right? So it requires some more thinking about data layout and programming to take advantage of it. And they have some SDK, as I mentioned earlier, software development kit that helps you with that. And we've done a lot of experiments with this. And these experiments are summarized, well, part of these experiments are summarized in this paper. This is really the first analysis, I think, of a real processing in memory architecture. And you can take a look at it. This is a shorter version of that paper. Essentially, we released these processing in memory workloads that are specifically for UpMem. We're interested in adding more. We'll add more over time, but you can see the breadth of the, let's say, domain and different benchmarks. The key, and these are open source. You can use them also if you're interested in your research. Feel free to contribute to them. And we have papers associated with it that you can find. So I think that maybe I'll give you the takeaways over here. The takeaway is that this existing, at least the current implementation of this UpMem architecture is very compute bound. What does that mean? it cannot do a lot of computation operations for multiple reasons. One is, for example, it doesn't have a multiplication operation. That's a design choice that people have made. I don't think there's anything fundamental to it, but they just didn't want to pay the cost initially in this iteration. Second, its frequency is much lower than existing CPUs and GPUs. Its frequency, operating frequency, is about 400 megahertz, let's say, as opposed to today's 4 gigahertz, right? And this is because it's just not easy to build efficient logic in a DRAM process because of the differences in fabrication. DRAM process is clearly optimized for the capacitor and memory density as opposed to fast and efficient logic. You get a lot of leakage, clearly. So there are limitations in the existing UpMem chips, but even then, on some of these workloads, we see huge benefits compared to an existing CPU and GPU. So that's also interesting, right? Given that there's no multiplication, very low frequency, you can write programs that can be much better than existing CPUs and GPUs because you have massive amount of parallelism that in the banks. And if you know what you're doing, despite the limitations of the architecture, you can gain a lot. Of course, on some other workloads, you do terrible because of these, plus there are some other issues that are in the implementation. For example, there's no easy way to communicate between banks today, even though they're in a DRAM chip, because they didn't, again, they couldn't do everything and they didn't think about it as much. So you have to go through the CPU, for example, if you want to communicate between the banks in this incarnation. That may not be very good, clearly, for some algorithms that require a lot of communication, right? And you may not be able to rethink that communication, but that communication is very fundamental potentially, right? So it's good to, I think, do these experiments to understand the existing architectures. But I think I find these experiments as very promising because despite all of these limitations, you have some workloads that gain a lot. Okay, and there are some insights that you can find in this paper. Okay. Okay, we've already talked about this. I'll mention one more thing. How much time do we have? 2 minutes, I think. Okay, maybe I'll mention it very quickly. So I think we've also been developing some other analysis methodologies to decide what parts of a function, what parts of a workload should you offload or not offload to a near data processing engine. I'll talk about it briefly. So clearly there are a lot of case studies that we have discussed and that are already exist that show that near data processing could be good, but none of them tackle the question of, given a function, should I offload it to a near data processor? It could be a general purpose processor in this particular case. So what we did in this study was a huge application study, huge for our purposes, more than 340 applications that we analyzed. You can see they cover a lot of domains. And we analyzed more than 77,000 functions in these applications to understand the bottlenecks. And in the end, we classified the bottlenecks quantitatively based on different metrics, 3 different metrics, like arithmetic intensity, misses per kilo instruction on a machine, and last to first miss ratio. You can look at the justifications, etc., in the paper. And the memory bottleneck in a function is classified into 6 different classes. And these 6 different classes behave differently in terms of what happens when you offload it to a near data processor. Some of them gain significantly all the time. Some of them never gain. Some of them gain after some number of processors on the memory side, for example. So basically the behavior of these six different classes is very different. And this can enable you to decide just based on these 3 profiling metrics, what should be offloaded or what could benefit from offloading and what could not benefit from offloading. I think this is interesting, but there's more work to be done actually in this direction. It's all open source again. You can download it, use it, make it better. Hopefully write even better papers about it. You were saying something? Enjoy it if you want. I don't know. Yeah, if you enjoy it, fine, sure. But I think there is more work to be done certainly in this direction. So clearly it's not automated, for example, currently, but I think there's more. Okay, maybe I'll mention, okay, this is not coming up anymore. This slide is old, but we've also looked at a very tough workload, which is sparse matrix vector multiplication on this processing in memory system, UpMem system. So I just told you that this UpMem system doesn't have a multiplication instruction. And we wanted to examine sparse matrix vector multiplication to see the boundaries, limits of the system. And now multiplication is implemented using shifts and adds clearly, which is really not nice, terrible actually. but we wanted to understand how it performs. It's actually not terrible, but there needs to be more work done. That's why we're looking into multiplication operations in these systems also. So figuring out efficient multiplication operations is also quite interesting in these systems. Okay, and you can find Christina's talks here. Samsung, as I said, this is another example of a real processing in memory architecture. There are papers written about it, and this is Samsung's public announcement. Their goal was to accelerate machine learning, probably inference to begin with. And essentially, they do add some logic into the DRAM. And essentially, they can execute multiply and accumulate operations, as you can see. This is very different from UpMem approach. UpMem cannot do multiply. Here, all they want to do is multiply. So you can see the different approaches taken by different industry folks. And this is kind of the, let's say, commands that you can have in this ISA, let's say, instruction set architecture that you can execute. Samsung claims that this is completely seamless to the software. I don't know. I guess it's not public, so we don't know. But it's a real chip that's published in ISSCC. This is the recommendation inference acceleration system of Samsung and Facebook. It's a module. It's a near memory approach again, but this buffer chip can do computations on the data that's gathered from these memory chips, as you can see. So it's interesting. There are some results. You can find a lot of information on these papers. Not necessarily deep information, I should say, but information. So SK Hynix actually is very interesting because these folks actually added even more hardware to the DRAM chip. I'm not going to go into the details of it, but their goal was also to accelerate machine learning, but also other applications. And these chips also have some sort of limited row clone functionality. Not exactly as we envisioned, but there's some that they sneaked in there. I wish they had snuck in more, let's say. And this is Alibaba's recommendation system. This is from ISSCC also, where they describe it's again a DRAM chip based. All of these are DRAM based, as you can see, and they're all modifying the DRAM chip in some way. Okay, that's all I know of basically. There are other companies that are doing this, but they don't provide as much information. They're more startups. Some of them are quite stealth also. Okay, but I think the future is quite bright and there's a lot more that can be done. Maybe we should start thinking about near memory processing chips over here. Who knows? Okay, so I think I'm at the end of this. As I said, okay, I think we can improve everything at the same time. If we just change our mindset and become more data-centric, we can improve energy efficiency, at the same time performance, and sometimes area costs, and maybe security also. This is more of a questionable thing at this point, but maybe by keeping the data local inside the memory, inside the storage, and not moving it all around, not exposing it to potential attackers, we can potentially improve security. But certainly energy and high performance at the same time can be done. It doesn't have to be a trade-off. I mean, once you move to more data-centric architectures, those trade-offs can start again, but we're basically wasting a huge amount of energy efficiency and performance today. Okay, as I expected, this is true. So we're not going to have time for the other two parts. Unfortunately, some people were interested, but we can talk on the boat trip or something. But we have, I mean, we have some old tutorials on this topic, but they're a bit outdated right now. Their fundamentals are there, but a lot more has happened actually since I gave this tutorial. In this tutorial, I was talking about reinforcement learning for memory controllers, but later on we published works on reinforcement learning based prefetching and reinforcement learning based storage system controllers also, which were the last one was at ISCA this year. So there's actually a lot of interesting things that are happening. People are also looking for learning-based caching methods, etc., which are more traditional, let's say. I think caching is also quite interesting from a learning perspective, because existing cache management policies, even though architecture community has been developing caches for 60 years or so, they're all heuristic-based, right? More recently, people have started looking at it from a machine learning perspective also. So I think that's good and refreshing. Okay, so let me conclude, or I can take more questions. So I think I argue that we must design systems to be truly balanced, high performance, energy efficient. That's the way to intelligent systems, I think. And I think we have to go through this route, Maybe there are other things, but we need to be data-centric, data-driven, and data characteristic aware. And what we have discussed mostly in this tutorial was we want to enable computation capability inside and close to memory. And hopefully this can improve both performance and energy by orders of magnitude. Maybe it can enable new applications and computing platforms that we don't imagine yet. I think there's a lot of potential here in terms of genomics. Maybe enable better understanding of nature. This is more speculative. This is what people in neuromorphic computing community has been interested in for a while, right? And I think there's some truth to that. And who knows what else. So I think the future is quite bright, but we need to work hard, let's say. And there's a lot more that goes into working hard, clearly. It's not just research, but also adoption issues. But a lot of the adoption issues here are also research, which is interesting. Okay. Yeah, I have this picture that is maybe, this is perhaps a computer, but it operates on principles that are very different from what our computers currently operate at least the way we understand it right now, right? Here, there's, as far as we know, there's no distinction between memory and computation as much. Again, as far as we know. And I don't claim that I know much. I don't claim that humanity knows much about this. Let me say it that way. Okay, let me finish it. I should acknowledge people. People who funded us. Hopefully they will keep funding us. And certainly my group who has contributed to all of this. And I've been describing their works clearly. And you can find some pictures, even though they cannot be here right now. And read about their research in our newsletters if you're interested. There's a lot more going on than what I just described over here. And I think everything I described, as much as we can, we make it available online. I'll stop here. Yes, any more questions? Yes, of course, go ahead. Oh, no.
So maybe you can provide us first with data-driven and data-aware.
Yeah.
And then maybe we can show which of the two is more important.
Oh, okay, I see. So data-driven, I think data-driven is basically you make decisions that are driven based on the data that you see, and you change your policy based on that information. That's my definition of data-driven. Does that make sense? Okay. So like humans are data-driven, I would argue that you see data, you interact with the environment, and based on what you see or what you experience, you change your policy. You don't decide, basically you decide not to touch the hot stove again, right? That's one example. Yeah, I think so, yeah. But I'm thinking of basically improving your policy over time based on experience. Data aware, I think it can be better called data characteristic aware. You make your decisions based on the properties of the data. You understand a piece of data and instructions for what?
By the application developer.
Yeah, potentially by the application developer or the compiler. Someone basically gives you that, okay, this piece of data is privacy critical. Make sure it doesn't get touched while some other programs are executing, right? Or something like that, right? This doesn't happen today, basically, I would argue. It doesn't happen even in performance characteristics, right? Somebody tells you the locality properties of this data, and then you place the data in a particular place based on that information. So that's the data aware or data characteristic aware. Yes.
I think driven is data from data. Sorry, driven is linked to the results. I have some results in my script. So having this data, I'll decide to do this or this. Data where is during operation or this the data in. Okay, this data has this specific property. So is that correct or not?
No, I don't. I think driven is really how I defined it earlier. So let's go back. Yeah, let's go back to this slide over here. So I think data-driven has been used in the other contexts. Yeah, certainly there are data-driven architectures, right? Data flow is an example of it, but I'm not using it for that context. Maybe we should come up with a better terminology. I'm all open for that. Yeah, so data-driven is really, okay. So I'm using it as opposed to human-driven decisions. You see what I mean? Okay. Okay, yeah. Yeah, and data-aware, I'm using it as opposed to component-aware decisions. You have a decision maker, controller, for example. It's making a decision based on the properties of the component as opposed to characteristics of the data. Yeah. I think it's best understood within that context. Okay. And to answer your second question, I don't know. Basically, which one is more important? I think all of these are important, frankly. And I think all of these should be done to become, let's say, more intelligent in terms of architectures. And maybe there's more to be done, but this is what I could imagine. Oh, okay, I see. Oh, okay. Yeah, again, I don't know the answer. I think both of them can have big potential, right? Especially, yeah, you may have a controller that can adapt greatly to the system workload device characteristics and buy you, I don't know, 10x performance and energy efficiency. But you may also get something similar by just characterizing the properties of your data and communicating it to it, and then doing something better with that. Yeah, it's very hard to, I think, justify a choice either way.
I have a question.
Sure.
I mean, of course, you've been working in this particular area, working for quite a while in this area. I mean, in your talk, estimate the case. Let's think about processing in memory. Processing in memory, I mean, I think your talk is convincing that it can be a fruitful avenue. But on the other hand, it's not quite clear that it will be the manna for everything, right?
Yeah, absolutely agree. Right. So it's part of the...
What you need is an architecture that can do both.
Yeah, I agree.
But what are the parameters of this hybrid model, and what should go to the PIM and what should go to the conventional stuff, and how do you break this system? Do you have an idea about that?
Yeah, I mean, I think that requires certainly more research, no question about that. But yes, I agree. Processing in memory is part of the equation. I think processing really needs to be distributed across the entire system. We should be able to. So your question, I think, is even broader, right? Because you have processors, accelerators, etc. They're designed in some way today. How should they change if they're also intelligent accelerators all over the system? And what part of a workload should execute where? Yeah, I mean, part of the things that we have discussed are trying to take steps in that direction, like what function should execute near memory, for example. That was the move work that I discussed toward the end. We can generalize that question. Instead of asking the question, what function should execute near memory, where should this function execute among these n different type of accelerators? I like that question, but it's a much harder question to answer, of course, than what function should execute near memory.
So in some sense, you say we first need to understand what are the limits of this, and then tackle the question.
Yeah. I think so. I mean, I don't want to impose an order necessarily. I think we can explore, let's say, concurrently, and both of them may be synergistic explorations. But yes, I think one is a bit harder because of the hybrid nature of it compared to simply exploring processing in memory. Yeah. Yes. Yeah, go ahead. Okay. Yeah, I know the paper, but I'm not sure if they really solve what Alex is asking for. Yeah, I will take an issue with that. I think there's a lot of academic work before Samsung published that paper that has looked at initial application level results.
Yes, but this is based on the actual chip.
Yeah.
So that's where the difference lies. Nobody takes our work, but people do things.
Yeah, I mean, our work is also actual chip. It was actually concurrently with that paper. Yeah, with district opmem, yes. Yeah. Yeah, but you're still looking for applications and where they benefit. Yeah. I mean, yeah, Samsung does good marketing, but that's a different thing. Sorry. But yes, I think it's a good step in the right direction, sure. Yeah, but I think the problem is much, much greater. It's not just application level studies. It's really having a methodology and framework where you can feed in, let's say, okay, these are my functions. Where should they execute, right? I think that's what Alex wants, if I understand correctly. That's much tougher to do. Yeah. Yes, please.
So I have a funny or tricky question.
Okay, sure.
I know the answer.
Okay, maybe you can answer it for me then. Then I don't need to. I can drink water and coffee.
Already there, and it's just programmed with one single instruction. What do you think this is?
We already have it, you said. You can buy a processing in memory device. Maybe I should open the floor for other people so that we can collectively brainstorm here. This is a tough question.
And you program it with one single instruction. Only one.
Anybody? At this point, I'm going to offload since we have the tutorial. This is an exam question, right? This you're calling it processing in memory engine. Now you're changing it though. I was going to say that, but I don't think so. Yeah, we can discuss it. So I think people make the argument that FPGA is a processing in memory engine. I would disagree with that completely. FPGA nicely combines processing and memory and enables you to configure things such that you can build a beautiful application specific or general purpose logic, whatever you want in it. But it's really not doing processing in memory, right? If you think about the FPGA itself, it's still, you still need to bring data into the FPGA, right? Yeah, but you still need to bring data from the DRAM into the FPGA, right? So it cannot operate without the bringing data part. Do you agree? In fact, even to program it, you need to bring in data. Maybe somebody, I think you agree. Yeah. I agree with that. I agree with that part, yes. Maybe you have a different opinion. Go ahead.
I think that to me, okay, the situation for the FPGAs, I think changed for the Versal engine.
Okay.
Versal engine is a later version of Xilinx.
Okay.
And this if I remember correctly, because it's quite recently, this first is very expensive.
Yeah, sure.
Yeah, it's a lot of, let's say, similar last level cast. It's not, you can think inside the FPGA.
Mm-hmm.
So the previous FPGA agent, as I know, doesn't have LLC, something like that, and several layers of memory hierarchy. So I think that's I think we have more opportunities. Okay, of course. Okay, maybe I don't know if it's for PIM for P. I don't know, but mapping out the application in different agents. And also the AI engine is, for me, resembles to TPU. And also AI agent will integrate with the new AMD processor together. So I think it's, I don't know, we'll have opportunity. Yeah, you call the versatile FPGA device. Yeah, actually, sorry. I made a mistake because Xilinx, stopped using this term a couple of years ago, but okay.
Like the FPGA device term.
Okay,
yeah, okay.
Multi-processor, multi-episode.
Sure.
I don't know what this. What to call it?
Yeah.
I think in this engine, I think it's some difference. This is my feeling. I don't know if I made a mistake, but
yeah. But I mean, I think we have some experience with that, and also what you said is the memory hierarchy. They add caches, etc. I think I wouldn't call that processing in memory, right?
And also, memory includes a lot of stuff.
Yeah, sure. But I think I agree with Georgi's description. You can emulate processing in memory in an FPGA, right? But yeah, to bring data into the FPGA, you have to keep moving data into the FPGA, right? Yeah. I think this may be a good discussion for later. So I mean, maybe I'll throw you another one, like the Cerebras devices, wafer scale device. Is that processing in memory, right? They claim that this is computing in memory. I partially think that their goal was actually to overcome the data moment bottleneck. No question about that. And they actually built a huge wafer scale chip where they have lots of SRAM, 40 gigabytes in the latest generation. And they have a lot of computation also. Clearly, they put a lot of memory near computation. So is this processing in memory?
Recently, I heard this actually question back to ask you. Apart Cerebras, also recently, I think 6 months ago, the British company GraphCore, I don't know if you're aware, fabricate the same Cerebras like chip, what it's called, wafer. So I think it looks as a trend in the industry. So I don't know if it is was difficult for me to program all this monster, but I think this wafer scale would be the idea, very good idea for processing memory. Have everything inside.
Yeah. But what if you, okay, sure. We should take this offline for dinner or beers or something. That's a good direction, I think, for brainstorming. Yes, please.
So I really like your idea of the distributed, for something like CPU, something in memory and so on. But have you considered how is it going to affect worst case execution time, especially important for the real-time system?
Yeah.
I'm just comparing it with the multi-core.
Yeah.
For the average execution time, it's great, but in some cases, it can end up 100 times slower.
The answer is I don't know, but I think there should be research on real-time or worst-case execution for data-centric systems. All of the research that I'm aware of on real-time or worst-case execution time is really on processor-centric systems. I don't think anyone has analyzed data-centric systems.
We barely know how to do it for a single-core system, and it's just.
Yeah, I mean, multi-core has the issue, right? Yeah, I mean, there are some works actually in multi-core. There's works that I've seen at ISCA and some real-time systems conferences. So there is some modeling that people have done for worst-case execution time. So it's.
a bit old, so it seems like Chiplet was supposed to get something more than this.
Yeah. Yes.
I'm just looking at the data-aware applications, but I don't get what kind of application works this, because in my mind, okay, I'm triggered by machine learning and that stuff, but actually, no one explained the properties of the data. It reminds me of something like refiltering the data before it enters the memory.
No, that's not what I mean over here. And we can go into it if people want to go into it. Anybody? I mean, it's okay. Maybe I'll give an example. Let me find these slides very quickly. So data was completely different, basically. It's not about filtering. Well, I mean, filtering could be guided based on the characteristic of the data. If that's the case, then yes, I would argue that that's data-aware filtering.
Yeah, my idea was like you collect the data and only the sum of that data can be considered by the application. So it's like you can somehow compress the data itself.
But how do you decide what gets filtered?
Yeah, that's fine.
Yeah, I think it depends on. Yeah. So okay, maybe I'll quickly suggest about what this data-aware, what I mean by data-aware. So basically, you have a let's say hardware architecture is the easiest to think about. I think you understand what you can do and with to each piece of data, and you take advantage of information that comes from the higher levels about the characteristics of data. I don't know if your filtering satisfies that, but basically, I think the problem today is if you look at the software-hardware interface, but this could be true for other interfaces also across the stack, is hardware doesn't get informed about much, let's say. So you have, at the software level, you have information about data structures, code optimization, access patterns, data types. None of that gets communicated to the hardware in the general sense, in the general purpose system. So in some domain-specific architectures, it's changing clearly. But in a general purpose system, you get instructions on memory addresses and maybe some hints if you're lucky. And these hints happen to be very, very specialized also. So the idea is, can we express program semantics or semantic information about data more generally, and also about computation, I think, going into the future, to the hardware? And that's the idea over here. I don't know if that makes sense. I mean, I can give you some more examples. And this is described by this paper that we wrote a few years ago. You can take a look at it. But okay, I think, yeah, for example, when you make prefetching decisions, prefetcher discovers access patterns today, right? It doesn't get told this data is not prefetchable, for example. There are some hints in the prefetcher, but they're not a general interface. Data compression, similarly, you don't know about the compressibility of the data. That hint doesn't get provided, or what kind of compressibility that you have in the data. That information doesn't get provided, whereas it could be very easy to discover by the software. What happens today is you have a compression algorithm in hardware. If it works, it works. If it doesn't work, it doesn't work. Basically, that's it. So that information doesn't get provided. So this is another example. Data placement also, based on the locality characteristics. You don't know the locality characteristics. You kind of discover it in hardware. If it works, it works. If it doesn't work, it doesn't work, basically. Basically, you don't have an interface to communicate all of this very rich information that you have, or that you don't have, but you can discover, to the underlying hardware. As a result, hardware needs to do a lot of work to discover partially this information, partially correct. So that's the situation we're in. And we want to change that by saying, okay, figure out as much information as possible from the top, communicate it with an efficient interface to the hardware, and the hardware can use it for any type of decision. It could be filtering of some of the data in the storage system based on some semantic information. Right? Does that make sense? And we have a bunch of examples over here, but probably you don't want to lengthen this tutorial. If people want to stay, that's fine. I'm fine with it. Yeah, but we have a bunch of examples as well. So yeah, okay. I'm going to stop here. There are a lot of slides over here. Yes.
The case that in data-aware, that the hardware and the software system don't communicate in our processes. I mean, are you also saying that not only it should be data-aware, but it should be control-aware, communication-aware?
Yeah.
I mean, does this go deeper than data?
I think so. I think so. I think we're looking at data. That's what we have concrete results on. But I believe so. I think we can communicate a lot more information about the computation structures that we have, for example. Again, data is part of what we do, but some computations may be more critical than others, for example, that could be communicated. Yeah, I think it actually spans across. This direction is actually much bigger, in my opinion, if you think about it that way.
But if you cannot do that, I mean, obviously, it cannot be a completely flexible system where you communicate.
No.
So one needs attempts to identify the 90% rule. I mean, what
Yeah.
is the 10% that we can implement in communication between the two subsystems that give us the more?
Yeah, yeah. I agree. I think there's more work to be done, frankly. Like in this work that I mentioned over here, we look at how to communicate properties of data, for example, with low overhead, minimal programmer effort, and as many general characteristics. So if the programmer wants to specify, I don't know, privacy, they should be able to do it, right? These were our goals in this particular case. And we did specifically for memory regions, for example. We have this abstraction that's called an atom associated with each memory region. And each memory region can be tagged like at the data structure level by the programmer or whoever is doing that tagging, let's say, based on whatever characteristic you want to expose to the hardware. So it's very general in that sense. But of course, I don't know how, we did not tackle the computation. So something similar can potentially be done for computation, communication, but I don't know of any work actually that looks at that. There's surprisingly not a whole lot of work in this area. Memory tagging work is interesting. There's certainly that work that has happened over years, but it tends to be very specific, not very general. Yeah. So I think what you are suggesting are great research topics.
A general chair of this conference, I will take my prerogative to sort of ask for everybody to give a big hand to Onur, so that the poor guy, after 4 or 5 hours of entertaining us, can go home and relax a little bit. Let's give him a hand.
All right, thank you.
Go home and crash.
Sure.